Hey, good morning. So welcome back to the last and of course most exciting day of the Liège Colloquium. And I'm happy well, we see our iconic picture here. And all the names. All right, so the full author list is here. Thanks. And Laure Respondy, she will open the last day with her keynote lecture on climate control of oxygen minimum zones. Laure, she's from Princeton, and we're glad to have this on-site meeting here with her and a couple of her group members as well. And we look forward to this keynote lecture. The floor is yours, Maria.
Thanks. Sorry, looked easy when the other did it, but okay, thank you. Thank you very much for having me. So I'm going to talk about climate control on oxygen minimum zones, and I will also present something about coastal hypoxia. And so I'm going to start, basically I'm going to showcase two studies, one about can we constrain those projection of oxygen minimum zones? And the other one, what is the risk of coastal hypoxia in the Indian Ocean, where you can see there are a few points, but there is, as I'm going to show, there is actually more points than that now. Okay, so let's start here. And we've seen that figure many times, and we've seen it many times in the past 10 years, or the previous version of that, where we have projections of the projection of models show a robust deoxygenation at mid and high latitude. This is the change in oxygen content by 2100. But in the tropical ocean, we have those uncertainties because it's not stippled, which means the models don't agree on the sign, uncertain magnitude of the biological and ventilation changes, despite robust change in solubility tied to warming. And the project that I'm going to show was really motivated. Can we go past that? Can we learn more? And I think we can learn much more than that message from our models. Now, during that presentation, I'm going to use three thresholds, a little bit like someone yesterday did that for her presentation. And very quickly, if we look at sublethal levels, we've seen that several times also. I chose 120 micromole per kilogram as like a measure of where, you have a significant impact on large fishes and crustaceans, for instance, in terms of stress. And I'm going to call that low oxygenated waters. And this is, those type of threshold are used for habitat boundaries. Then I'm going to use hypoxic waters at 60 micromole per kilograms, where you have increased stress, but also you have, according to a recent study, you would have some denitrification happening on microenvironment on particles, so potentially N2 emission also in that range. And then the core, which I call the core, is delimited by 20 micromole per kilogram. So those are, which excludes, most of microorganisms, a lot of those microorganisms in that range. So I'm going to look at those three to showcase the differences, because the idea is to look at the oxygen minimum zone in that oxygen framework to see, can we make sense of those contradicting trends in the models using a more comprehensive oxygen framework. So what control the oxygen minimum zone? Well, they are confined to the shadow zone of the thermocline and what is right below the thermocline. And in that sense, they get the supply of oxygen to, here I'm showing in the example of the Pacific, you have a subduction at mid-latitude, and you have the ventilation by the subtropical cells that provide oxygen, that shoulder and provide oxygen to those low oxygen, oxygenated waters. Now, in the core, it's slightly different. You don't have direct advective pathways. That's the definition of a shadow zone. And what is controlling here the supply and the demand of oxygen is really a slow supply by turbulent mixing, so vertical and horizontal turbulent mixing. So for instance, in the equatorial band here, it would be the jets, it would be the turbulence, the shear mixing, it would be tropical instability waves. And you have a biological oxygen demand, which is partly fueled by mixing, meaning if you change mixing, you change the ventilation, but potentially you would change the supply of nutrients to the surface, the production and the oxygen demand. So you have that balance with through mixing between ventilation and respiration. Okay, so what can we expect in the future as the ocean warms? You expect a weaker ventilation of the subtropical cells, so potentially lower supply to the low oxygenated waters. You also expect weaker mixing, which would have potentially opposed effect on the core of the OMZ with reduced ventilation and also reduced biological demand potentially. And in between the hypoxic waters are kind of, I make those two end members, but then you have obviously a spectrum between those two extremes. Okay, so I'm going to start by looking at the climate models, the latest generation that we have in the tropical ocean, and show that there is actually a diverging fate between the OMZ, the low oxygenated waters, and their core. And this is some work led by a postdoc, Julius Pusecki and Sam, who had a poster here. Okay, so we use 14 models of the CMIP6, which is the latest Earth system model generation. And what I'm going to present here is the high emission scenario. So with this little name, SSP585. And I'm going to start with a zoom on the Pacific, although at the end I will show that it's very similar in the other basins. So this is a comparison of the observed oxygen minimum. So this is the extent, the maximum extent of that oxygen value. So this is the maximum vertical extent of the core in the data, and this is 60 micromolar, and this is 120 micromolar, so the low oxygenated waters, compared to the model median here. So it captures relatively well the low oxygenated waters extent and the hypoxic extent. You see that it does underestimate the core extent. And in terms of volume, for low oxygenated waters, they are within 25% of the observations. But there is like a mismatch in the volume, about 100% for the core, for instance. You see also in the district, you do see, for instance, the model median, the models don't represent very well that patch here of core, but here I'm gonna mostly look at the tropical 30-30, so that exclude most of that part actually of the core. Also, what I want to point out is one of the features that is different is in the observation, you see that we treat like the two lobes between the northern and the southern core. And this is tied to the equatorial dynamics, the equatorial undercurrent in the Pacific, which is usually not very well represented in models, but I'm going to show later very briefly that some models are actually doing much better than others in that sense. Okay, so if we look into the future, in that model median, we see that we have three regimes. Actually, if we look at the core, and this is as a function of time, you see the evolution of the core volume. And this is the median with the interquartile here. And you see that actually in the core, it's contracting in most models. It's relatively uncertain. It's a weak contraction, and it's uncertain in the sense that some models show a near zero changes of. I really like the metric of the Baltic Sea as a volume metric, so I put that here. It's that median here is about 50 Baltic Sea. So it's small for the Pacific, but it's still a relatively large volume. If we go now to the low oxygenated waters here at the bottom, you see a robust expansion across all models. It's very clear. If you look at the low oxygenated waters, the one that are used as as a habitat boundary, they show a robust expansion of about 500 Baltic Seas by the end of the century under that high emission scenario. And in between, if you pick the hypoxic waters threshold, you have a near zero change. And I'm going to show later that you actually have a redistribution. It doesn't mean that it's not moving at all, but it means that you have some redistribution between the OMZ core, which is contracting, and the expansion. You have some like redistribution. Now, I'm showing those like 3 thresholds, but now if we try to just look across all thresholds, and here I'm going from 5 to 160, and you actually see that if you look at the model median with the interquartile, you have a regime where you have contraction at low thresholds. These are relatively uncertain in magnitude and could be very, very weak contraction. Then you have expansion, very robust at high threshold, above like 100 micromole per kilogram. And in between, you have that regime where it's just transitioning from the contraction to the expansion with a near zero change and some redistribution. What I would like to point out here is that most of the study that were published before, including my own, we picked those thresholds to look at the models, 60, 80, 40. And obviously you see that if you pick only that threshold, the message you get is we have no idea what's going on. The models are all over the place. Some of them are increasing, some of them are decreasing. But actually, if you put it back in that larger framework, true, we have some uncertainty exactly, on the magnitude, so it becomes uncertain. But I think if we look at a bigger picture, we see a picture emerging here in our models. It doesn't mean they are perfectly right. It just means they converge towards something. Now, if we look what controls that, change. And here I'm looking now at the oxygen trend. So it's the oxygen content, not in the whole tropical Pacific, but kind of in an onion peel or like a nested shell. It's really the change in oxygen that control the change in volume. So for instance, here in the core, if it's contracting, you have more oxygen. And it's really between the volume at the start and the volume at the end, how much oxygen has been provided to that change to explain that change in volume. So the black here is the change in volume. You see more oxygen provided to the core, less oxygen provided to that, low oxygenated waters, and in between kind of near zero changes overall if you integrate. Now, if we look at what controls that, in orange you have thermal changes. You see, as we expect, they decrease oxygen in all those volumes in a relatively homogeneous way. But then really what control that shift from contraction to expansion is the non-thermal part, so ventilation and biology, which could be expected, but it's really clear. What also you can see is most of the uncertainty is tied to that non-thermal contribution and not to the thermal contribution, which is consistent with the picture we have, I think. Okay, so let's have a look at, ventilation, biology. Can we go a little bit further? What is going on in those models? And I'm going to start with the low oxygenated waters. This time I'm showing you a map of the change in oxygen, just to give you a sense. And you do see a decrease in oxygen in most of the, the waters that are ventilating, that pathway that I was showing here and here. And I'm not showing it here, but you also have older ages in the model, and this is consistent with lower ventilation. And here is another way of showing that. If I show the change in the volume of those low oxygenated waters versus, versus here the change in the subtropical strength, you see that the larger expansions are associated with larger change in the subtropical ventilation, the strength of those loops that bring oxygen to the system. On the other end, if you see here the smaller expansion, the models that show smaller expansion, you have a smaller change are associated with smaller change in the subtropical cells. And this is consistent with some work that Dutheil published to link the subtropical cell strength to the upper ocean oxygen content in an ocean model, in a hindcast past simulation model. So really what controls that low oxygenated water volume is the ventilation of those subtropical cells. And you do see some uncertainty in that change in those models, obviously. Now, so if we summarize, a little bit what's going on in those waters, we have a decrease in ventilation, which means an oxygen, no MZ expansion. Now, if we go to the core, here I'm showing the change, again, in oxygen. And if we zoom in on that core, you do see a slight increase of oxygen in the core, and younger ages, which I'm not showing here, but younger ages in those waters that switch from being not in the core to being within the core. And this is consistent with, some papers that have been published in the past that show that there are changes in the renewal of, maybe more renewal of intermediate waters, and most probably what's going on here is the changes in mixing, which means if you have your core and the oxygen is supplied by mixing, but you change the ratio of the waters that go in, meaning you supply more of this, ventilated waters compared to the deeper waters, for instance, you will change the age and the oxygen content, even if you reduce mixing, just by changing the ratio of the waters that are provided to the core. And this is definitely what our models are doing. Is it what is happening in real life is another question, but that's definitely what the models are doing. Now, the core contraction is also consistent with reduction in biological demand. And this is a figure of the change of the export production at 100 meters in the model median. And you do see a wide decrease of oxygen, of export of particulate organic carbon. So which, we don't have really the respiration in the model, so we can't really look at what they're doing, but clearly they should have a lower biological oxygen demand. Those two things are consistent with the sign. I can't tell you which one is more important than the other in controlling what's going on, because I don't have the information in that ensemble here. But what I find very interesting, if we zoom in on two models, and here I'm showing as a function of time, the change in the core volume. So you see most of them are going down. The change in export over the full basin, and then the change in export just over the core. And, obviously the oxygen in the core is the oxygen demand integrates the pathway, like how much was, consumed. But also on like a 50-100 time scale, it's probably going to be very driven by what is local, because there is no direct advection into the core. It's really tied to, more local effect in the core because it's so protected from outside influence. And now I'm comparing two models. They are the same exact Earth system model, CANI SM5, but the only thing that changes is the biogeochemical module in the ocean. And we have a more complex one and a simple one. The physics is the same, the circulation is everything is the same except the biogeochemistry, the ecosystem model. And you see that the simple biogeochemical model projects a much larger contraction of the volume of the core, associated with a much larger, reduction in export in the all of the basin compared to the more complex model, and about like 10% versus 30%, so a three-time fold change. And I think what that tells us is that there are in that complex model, there are some feedbacks that stabilize the core and stabilize the export. One example could be what Zuhair, for instance, Lashkar showed in one of his papers. When you have denitrification, when you reduce mixing, yes, you reduce, the supply of nutrients, but then you also have a feedback through denitrification that will regulate the supply of nitrate and make it a weaker feedback. So that is probably what is going on here. More complex biogeochemistry probably say that it would be a smaller change. So maybe if the more complex model, hopefully we think is more representative of nature, that would suggest that our projection would be, the evolution of the OMZ would probably be in the lower range of our prediction. Okay, so what is going on in the core? We have increased ventilation in the core, and we have probably also reduced biological demand. And what we see is that you know, we tend to say physics is the main driver. It's true, it's a main driver of a lot of things in the evaluation, but in that case, it's obvious that the magnitude, understanding the biogeochemistry will be very important to understand the magnitude of the response. Okay, I'm gonna try to present a little bit of, you know, what could be some impacts, like spatially, because oxygen framework is great. It allows us to, you know, make some, maybe to have a consistent picture, but what does it look like if, you know, in terms of habitat, for instance? And here I'm showing the upper boundary of that low oxygenated waters and how it changed in depth. So red is shallower. So you see that you have a 25 to 50 meters shallowing of those low oxygenated waters in those regions. In the median, so potentially some contraction of the habitat here. If we look at the core, we see that we have a contraction, so a deepening of the core here and here of about 10 to 20 meters. Does that mean maybe less nitrous oxide evasion? It's not like direct, it's not that simple because you need to hold the dynamics, but maybe. And then I'm showing here the hypoxic level where you do see some shallowing here, but some deepening where the core is located. So a redistribution of the volume, basically you have less volume in that band here in the equator, but more volume in other places, which might be very relevant when you think about ecosystems. The fact that the total volume is not changing doesn't necessarily mean you're not going to be impacted locally. Okay, now that was the Pacific. Now if we look at the other basins, we see those three regimes. Again, that's the tropical Indian Ocean and that's the tropical Atlantic Ocean. And you see in all the basin, you have a contraction regime in all models, broader flat, like oxygen range for the tropical Atlantic. Then you have a transition regime with very small changes and then an expansion at a higher, so all the models at higher thresholds. So what the models are telling us is, I mean, that's what they project. They project contraction of the core, expansion of those low oxygenated waters will represent the habitat boundaries, and in between a near zero change, a transition basically from those two regimes. Now we have uncertainties on the magnitude. We still have, you know, uncertainties on where that crossing between contraction and expansion might be. And again, that's for high emission scenario. So, okay. Now I would like to point to you quickly how some like models can be very different. And this is, you know, a model where the core is very small compared to the observation. The black line is always the observation here. And then the colors are the models. You have one where it's way too big. Most of the Pacific is covered with a core, and then one where it's, you know, almost right. And here, I'm going to show that if we compare you know, what is going on at the equatorial band, in particular here, whoops, that equatorial band here, where some of them have the two lobes, whereas some don't have those lobes, that makes a difference in your projection. And here I'm showing very briefly another study where this is observation. This is a section of velocity. So you see you have your equatorial undercurrent going west, going eastward. And then on the side at the equator, you have some jets, alternating jets. And the OMZ in steeple here is like shouldering that system. In coarse model, it's a 1 degree. You see that very fat kind of equatorial undercurrent, very like weak jets and an oxygen minimum zone. You have so much diffusion around it that it's eroding the oxygen minimum zone. Comparing to an eddying model, 1/10 of a degree, where you have a structure that looks very much like the observed one, and the OMZ really shouldering again, much more like what we observe in nature. And if I compare those two models, that coarse model has actually, the variability is 30% stronger than in the eddying model, which suggests that this type of, and in the paper, we explain why it makes it more sensitive to change. So again, you know, I told you with the biogeochemical changes, when you have a more complex model, it might probably dampen some of the changes. Here it's the same. If you have a more realistic physics and dynamics, maybe it actually also stabilized the OMZ and tune down the changes. Okay, so the OMZ response falls into three regimes: expansion, contraction, near zero change. That oxygen framework, I think, explains some of the discrepancies that we highlighted in prior work, because we were right there at that hypoxic transition where our models don't agree, although they agree on the bigger picture. More realistic biogeochemical model and mesoscale dynamics improve the OMZ and stabilize its response. And this suggests that the OMZ response might lie actually in the lower range of our projection. And okay, some impacts, which I didn't go into much detail here, but that open a door in looking at. I want to finish with a few slides on a study about the risk of coastal hypoxia in the Indian Ocean. This is the picture where we see those red dots here. And my postdoc Jenna and a student of mine, Mathieu, have been leading that study, working on hypoxia. And this is, so they started with a review of the literature and found about 108 events. So in the paper, which was accepted, there is a table we tried to keep the same format at the Brightberg to, so those can be maybe added simply. You see that a lot of those events are actually yellow, which means they are tied, they were attributed to upwelling. And so you do see that a lot of the hypoxic events in the Indian Ocean are tied to natural, variability and not necessarily eutrophication yet. So why is, the Indian Ocean at risk? Well, it has 30% of the world population, potential for a lot of eutrophication, but it has also a natural oxygen minimum zone and strong seasonal and interannual variation in upwelling and downwelling, tied to the monsoon and what is the Indian Ocean dipole. So kind of an El Nino mode of variability. And here I'm just illustrating that during positive phase of the Indian Ocean dipole, you have a wave, a Kelvin waves that propagate here around, and you have a second train also here, which means that during those positive phase, you have upwelling in the Bay of Bengal, and then in the Arabian Sea, you will have downwelling followed by upwelling. And there is one model experiment that says positive IOD phases limit hypoxia here at that dot. So we wanted to see, can we use observations to learn more about this? And so we took all the oxygen profiles from the World Ocean Database in a coastal, along the coastal shelf. These are the value integrated between 50 and 200 meters. This is the, the amount of profile, as we see that gap here that we've seen many times. And then we categorize them hypoxic, vulnerable, and more than 80 micromole per kilogram, about 4,000 profiles. But then the question is, when do they occur and why do they occur? And seasonally, if we look at the Arabian Sea, here are like a mean of all those profiles in summer and in winter. And you see that a lot of, there is a lot of variation. And here you have the hypoxic threshold just seasonally. So the risk increased a lot during summer, and that has been, it's not really new. That has been shown before in the Arabian Sea. In the Bay of Bengal, it's a much, smaller impact of the monsoon. But now if we go to looking at the Indian Ocean dipole, I'm probably gonna, I don't know, I don't want to take too much time, but here if I look at this is the seasonal distribution of profiles. So in summer, if we focus on that bar, you have a 50% chance to have a 50% likelihood to have an hypoxic profile in the Eastern Arabian Sea, whereas in the Eastern Bay of Bengal, it's only about 20%. Now, if we look how it's modulated by the Indian Ocean dipole, you see that it's reduced during Indian Ocean positive phase of the Indian Ocean dipole, and that's consistent with that earlier study, which was in that region. Now you see that no change really during the negative phase. If we go to the Eastern Bay of Bengal, however, you see that during positive phase, you have an increase in the risk from 20% to about 40-ish%. In both seasons, actually, you have an increase, and during negative IOD, you almost have absolutely no, hypoxia in that region. So the Indian Ocean dipole is modulating the risk of hypoxia. Why? And because actually, if you look at upwelling, downwelling due to those waves that I've been talking about, it's really in phase with those risks. So we established a map like this, and I'm happy to talk more about it if people are interested. And I'm going to finish here. eutrophication and the impact of humans is probably going to become much more important in the Indian Ocean. So looking forward, natural factors are only going to be reinforced by human impacts. Thank you.
Great. Thanks a lot, Laura. Very stimulating presentation, and also bringing our attention to the Indian Ocean, which will be followed in the next few talks here as well. Questions? Yes, please.
Thank you very much for the talk. It was great. I had two questions. Actually, you already answered one, so I'll go with the other one. We saw in the past week that most models are underestimating actually what the observations see in terms of trends in oxygen. And I was wondering, may it actually be the case that the simpler models are doing a better job than the more complex models from what you were saying before?
You mean the simpler, okay, so in terms of dynamics, I think this is a very compelling case where no, the more simpler model are not doing better because okay, so in terms of dynamics, now in terms of biogeochemistry, it's really, yeah, that's a good question. Although I'm not sure the difference between that 1 to 2% that we've seen the observation in our models come from the biogeochemistry specifically because most of that percent is at middle, it's in those waters at high latitude, the ventilating waters. It's not necessarily in the OMZ, most of that, percent of the total oxygen. However, it's true if you have the wrong, ventilation, then it will impact your OMZ. I do think though that nature tends to have, at first, at least at the beginning, some feedbacks that are regulating the system. To me, that makes sense that, it makes sense. Then how those are going to evolve in the future, that's a different, it's true, you could have some like runaway effects, but where is it? But the fact that, you would have a stabilizing mechanism for the system is not completely crazy to me. I don't know, I think it makes sense.
Yeah, I had a question too. I was wondering if this contraction of the core, it had been observed in observations or
So if we had so good observation to observe at that level, it would be great. I know that there are some local observation. It's really hard to have a vision of the total core. But clearly, for instance, in the Indian, there are places in the Indian Ocean where you see a contraction, and other place where you see an extension. I haven't tried to piece that out exactly with the threshold on the core. I don't think we have enough data to do that yet. Maybe with the fantastic GODAT thing, we will.
Thank you, Laura, for the great talk. So you showed the influence of the representation of the biogeochemistry with this graphic, and you mentioned denitrification. So my question is, how do you think that the threshold, the switch from oxidation to denitrification in the model, so the parameters that you put will influence that figures and also the different regimes that you have shown?
Yeah, so I didn't put anything in that model because it's a Canadian model, it's not mine, but that's a good question. And so here in that case, in the simple model, there is no denitrification. And the other one, there is denitrification. However, you're right, by comparing different models that we have in my group, we see that depending the threshold that you put for your switch to denitrification, it does impact your change in volume. And actually, you're right, it's probably part of the reason in that spread here, and although I think there is also a lot of difference in the ventilation across those models. But yeah, there is a very different parameterization of denitrification across those models. Yesterday we saw some presentation about the iron, from the sedimentary. Some of them have a representation of that, but a lot don't. So there are a lot of different things going on between those different.
Great, thanks a lot
for the
questions. Thanks, Laura, for the exciting and stimulating presentation, and also for the introduction of the Anne-Moret metric of the Baltic sea volumes. Might be good to have, or maybe there are other areas of the world as well we could use, so to have diversity. And we move on to the next speaker. It's an online presentation, Damodar Shenoy. Or Shenoy, I'm not sure, I probably certainly pronounced it wrongly, excuse me. Can you hear us? And
I can hear you all, and can you hear me?
Yes, perfect. And so the floor is yours.
Let's click on this, yeah. Good morning to you all, and it's good afternoon here at the moment in India. So at the outset, let me thank the organizers for giving me a chance to present this work. And I'd also like to thank my parent organizations, CSIR and the Ministry of Earth Sciences, which have been funding this particular time series observations that we have been carrying on for the last 24 years now. And the title of my talk is Interannual and Decadal Variability of Dissolved Oxygen of the West Coast of India, results from a time series study. My co-authors are Suresh, Hema, Anil, Sibi, Suhas, Gayatri, Dr. Nakvi. I'll begin with a bit of introduction about the area. I think people have been talking about it since the last couple of days, but nevertheless, let me touch upon and try to highlight in what way the region I'm talking about is different from the rest of the area. So the Arabian Sea, the very well-known feature about this is the seasonal reversal of winds, and have the northeasterlies, during which we have the winter convective mixing, which is very active in the northern Arabian Sea, due to which we have again productivity happening in that spot. And we have the southwesterlies, which is shown over here, wherein you can see active upwelling happening off the Somali and the Oman coast. At the same time, a weaker upwelling, which was just touched upon by Laura, and a little bit of it, I can go a little bit more detail about how that works. So we have a weaker, and this, as she mentioned, it is remote coast. Nevertheless, we can see chlorophyll buildup coast on the Western Arabian Sea side as well as the Eastern Arabian Sea side. So from the main point of view, the upwelling that happens off the coast of India is much, much weaker. I'll go a bit more detail in that. Now, right side is the panels wherein you can, this is basically the climatology that was derived from around 7 to 8 years of data between 1997 and 2004. And on the right-hand side, we can see a temperature, oxygen, nitrite, ammonia on the left side. On the right side, we can see salinity, nitrate, nitrous oxide, and hydrogen sulfide. So what basically happens is you have the thermocline waters, which basically come onto the shelf during the southwest month, and that goes on from June to September. And what's shown over here is the temperature wherein you can see low oxygen, low temperature waters with low oxygen coming and residing on the shelf. Now let me point out over here the upwelling that happens along the west coast of India or the Eastern Arabian Sea is spatially and temporally variable. It starts as early as March, April of the coast of, of the southern tip of India, that is of Trivandrum and Cochin area, and it travels up north gradually, covering up to Gujarat and Mumbai area by around July, August, September. Of Goa, the upwelling is most predominant during the mid of June, but mostly during July, August, and September, as shown from the temperature. And at the same time, we have the southwest monsoon, which brings in a lot of rain along the entire coast, and that rainfall comes off, and you can see in the form of a low saline lens that's shown over here. The station that this is basically is the CATS G5, for which I'm going to show 24 years data basically on temperature and dissolved oxygen. And you can see because of the nitrate, high nutrient conditions, you get productivity due to which the oxygen is further consumed in the already low oxygen waters, and that basically drives the system to denitrification, and wherein you get nitrite and you get high concentration of nitrous oxide. But compared to the open Arabian Sea, this system the open Arabian Sea only goes up to denitrification, whereas all the way up to split reduction. So there are certain years wherein we have been finding high concentrations of H2S in these waters. So due to which this region is kind of a hotspot for nitrous oxide, dimethyl sulfide, and H2S. And this region occupies an area of around 180,000 square kilometers. Coming into the details of the time series work that we have been doing, this station, the CATS G5, is roughly 12 kilometers of Goa. It's a depth of around 27 meters. This was established in 1997, basically to look at how the land and the coastal ocean interact. But then we realized that we need to do some long-term measurements to see how the entire system changes. So the measurements that we have done basically are monthly to seasonally. Whenever funding was available, we could do monthly observations, whereas sometimes when funding was less, we used to manage and somewhat do seasonal observations. At the same time, going out, and most of the observations are done using a mechanized boat. So going out during the monsoon was very, very difficult, actually tough, we could not go out. So the June-July observations are mainly available from some of the cruises that we used to go out on. And during this measurements, the main thing, the temperature was done, measured using a Seabird CDD. We were using a portable 911 or on board we were using SB25. Plus these CDDs were sent back to, sensors sent back to Seabird every 2 years so that calibration can be done of those sensors. The oxygen shown here is which I'll be showing here is the Winkler method, and the hydrogen sulfide is done by spectrophotometry. So the data which we had, I segregated them into surface and bottom. Sometimes due to the CTD being a bit lower due to rough weather conditions, you could take around 3 meters data. So the surface data is taken up to 3 meters, whereas the bottom data is taken from 23 to 26 meters. Just a bit of definition for clarity. The seasons which we will be talking about are the northeast monsoon going from December to Feb, spring into monsoon from March to May, southwest monsoon from June to September, and fall into monsoon from October and November. Going on to the results, and shown here on top is the absolute temperature measurement, and down panel shows the temperature anomaly. And on the x-axis, basically what we have is the cumulative months, on which I have overlaid the years so that it's more clearer and easy to understand. So what we see over here is the data on temperature, sea surface temperature going from 1997 to 2021, and we see a gradual increase in the overall temperature. And from the slope, we can make out that there's an increase in it. The annual rate of increase is of the order of around 0.042 degrees Celsius. And we see a similar thing also in the case of the anomaly. Let me point out a few, even though it's surface temperature, you'll find some of the points over here are much lower than what they need to be. These are basically the anoxic events that happened during 2001, 2005, and 2009. 2001 was a very strong anoxic event during which I think the entire shelf was covered with very low oxygen waters, and the prawn industry during that year nearly collapsed. But if you look at the seasonal variation, it shows a more interesting result. Shown here are the 4 seasons, the declaration 4 seasons: the northeast monsoon, the spring into monsoon, the southwest monsoon, and the fall into monsoon. We can see compared to the northeast monsoon, spring into monsoon, and the fall into monsoon, you see a high rate of warming observed, marginally higher during the spring into the northeast monsoon, the southwest monsoon, and are showing a little bit higher warming rate compared to the spring into monsoons. One of the reasons maybe if you look at the base values of it, I think the spring into monsoon being the summertime, usually the slope may not rise that high. But nevertheless, overall you can see an overall warming in this particular region. And if you look at the oxygen profiles, again, this shows a marginal decrease. Top here shown, the top panel shows the surface dissolved oxygen from 1997 to 2021, 24 years, whereas the bottom one is the DO anomaly. And again, as I mentioned, you can see an overall decrease as shown from the slope, basically showing that we have an annual loss of around 0.0046 ml per liter. This basically works out to somewhere around 0.2 micromole annually. And if you see the seasonal variation, which is again interesting, you can see that overall in the 3 seasons, the northeast monsoon, the spring into monsoon, and the fall into monsoon, you can see a fall. Whereas during the southwest monsoon, you can see there's a marginal increase, there's a gain in the liquid of oxygen over the years. This, we believe, may be basically because of productivity, but then at the same time, it may also have some connection to the overall upwelling that's happening in the region. Now, this is as far as the surface temperature and dissolved oxygen goes. If you have a look at the bottom temperature and dissolved oxygen, they show a very interesting feature. To begin with, the bottom temperatures show a much larger variability, as you can see, also shows a lot of segregation. While we see in both cases seasonal variability, the trends overall talk about the overall general increase as it goes on. So again, in the bottom temperature, you can see the increase going on from 1997 to 2021. But then you can see the bottom temperature gain is much higher. It's nearly double than that what we see in the surface temperature. And the same is also seen for the anomaly. The temperature seen here in the below the fit is basically the temperatures during the southwest monsoon when the upwelling happens. But you can again see the trends coming out over here, which is more clearer when you look at the seasonal trends. And there again, we can see that the southwest monsoon, the warming is much more compared to the northeast monsoon, the spring into monsoon and the fall into monsoon. So you can see a higher rate of increase observed during the southwest monsoon. And this again has connection to what Laura explained earlier. And I think here we get a nice connection between what the models are doing and what the observations are actually showing. But then we need to see again, because it doesn't totally match. There is around 80% is what I'm finding matching between the models and what we have. If you look at the dissolved oxygen profile, this is very different from what we got for the surface. In the surface, we find that overall there's a deoxygenation happening, but in the bottom, we find an overall increase in the oxygen profile as we move over the last nearly 2.5 decades. So you can see, compared to the surface oxygen, in the bottom, we can see a gain, and the gain is of the order of around 0.024 ml per liter, which works out to roughly around 1 micromolar. This is roughly 5 times what is lost in the top. Now, what's basically the cause of this? The basic cause of this, we believe, is a little bit more clearer when we look at the profiles of it, seasonal profiles of it. You can see that during the northeast monsoon, there is an overall loss, whereas during the spring into monsoon, fall into monsoon, and summer and the southwest monsoon, you're having a gain. Maximum gain is actually observed during the southwest monsoon and the spring into monsoon. This basically has a connection, the southwest monsoon has a connection to the overall decrease in the upwelling that's been observed, as I'll show in the next slide. So what we see is during southwest monsoon, you find overall there is an increase in the bottom dissolved oxygen, whereas we believe, and since the southwest monsoon basically lasts between June to September, the main upwelling event and productivity lasts from somewhere around August to September, but then a part of it also falls in the October part. That's why we believe that you find a very light increase in the DO during the October part, but during the spring into monsoon, we also have an annual occurrence of the Trichodesmium blooms, and we believe that might be one of the reasons why we find a little bit gain that's happening during the spring into monsoon in the bottom waters. Now, one of the things that INTRIG does was what controls the anoxia in this particular region. And what's plotted over here is the hydrogen sulfide. So what we see, pardon my spelling mistake over here. So on the x-axis, what we have is the hydrogen sulfide, and basically this is the maximum H2S observed at the CATS G5 location over the years. And you can see overall there is a decreasing trend. And earlier years, we were a bit confused as to what's happening, because initially it was thought that it's the anthropogenic impact that's driving this. But later on, since we also did some work in the rivers, we realized that it's just not much amount of the nitrogen comes out. It's mostly taken care in the rivers, and only around 0.1 teragram of nitrogen comes out in the. And again, it brings back to the point that Laura explained earlier, is that the basic control of the hypoxic and anoxic events here is the natural variability. But then this particular figure of H2S matches very well with the increase in the bottom dissolved oxygen. And we also did some modeling work with Suresh and his group, and again it brings back to Parvati's paper, wherein she explained that the positive IOD years will be the years wherein you will not get that intense anoxia, and the negative or the neutral IOD years will be the years wherein you may or you will get H2S product, but it doesn't have to be going accordingly that way. If you look at the years over here, 1997, 2006, 2012, 15, and 19 are the positive IOD years. The only exception here is the 2006 one, wherein we do get H2S. Similarly, in the negative IOD years, 16 is supposed to be, only exception over here is the we get, and similarly in the negative IOD years, except for 1998, 2009, the remaining years. So overall, what we find is that the trends match pretty well with the IOD events. So to summarize, we find large seasonal and internal variability is observed in temperature and dissolved oxygen concentration at the CATS T5 site. And you find that the top layer is definitely warming up and is expanding and is deoxygenating. So surface waters seem to be warming at a rate of 0.042 degrees Celsius, associated with the deoxygenation rate of around 0.046 ml per liter. This works out to around 0.2 micromoles per year and roughly around 5 micromole over 25 years. And the bottom waters are warming at a rate of 0.076. They are warming a bit higher rate, but is basically associated with the reduced upwelling that happens in the region, and is associated with the gain of DO rate of around 0.024. That works out to around 25 micromolar over around 25 years. So this is what we see in terms of the observations, and we find that the anoxic more or less tend to match with the bottom DO as well as with the IOD events. I have not shown the chlorophyll profile, but then the general trend over there again is that we find a reduction in overall chlorophyll that's happening. And what we are focusing upon next is how does this influence the phytoplankton and the zooplankton population in the region. Thank you.
Thanks very much, Amodha. Very exciting to see this great data set as well. And I think that's another great addition to the Global Ocean Oxygen database and atlas that we all together want to develop. And also great to see that there's some consistency between models and data. So that's an excellent step forward. I'm afraid we have to move on. Thanks for your presentation, very much appreciated. And well, stay in contact for this GLODAP development and combining data and models. I think that's an excellent effort. Thanks a lot. Next speaker, it's on the Indian Ocean again, Parvati Valavathailam, and she will present, look also on the Arabian Sea and looks at its response to climate change. The floor is yours.
Okay. Okay. Yep. Okay. Okay. Good morning, everyone. My name is Parvati. Today, I'm going to present a part of my research, which I carried out at New York University in Abu Dhabi. First of all, I thank this wonderful colloquium organizers for making it possible to present my work in person after 3 years. So the title of my presentation is A Downscaling Approach to Understand the Response of Arabian Sea Oxygen Minimum Zone to the Climate Change. Okay, so just to give a recap, I think I don't have to give a lot of introduction. By now, most of you must be familiar about the peculiarities of Arabian Sea. So we have a landlocked northern boundary that brings in seasonal modulation in the surface circulation. So as you can see, during the summer monsoon, which spans from June to September, we have a strong southwesterlies that blows from the ocean to land. So in terms of biogeochemistry, we have very strong surface blooms, which is coming from the coastal as well as offshore upwelling. So this covers a large area of the Arabian Sea. As shown here, this is a satellite imagery of surface chlorophyll. Whereas during the winter monsoon, that is from it's from December to March, we have strong northeasterly winds. So this is completely of different characteristics. So it brings in a very strong convective mixing that is much intense in the northern part of Arabian Sea. So its signatures can be seen in the surface chlorophyll image here. So together, these two monsoon seasons make Arabian Sea to be one of the most productive regions, so which is good for fisheries. But when it comes to the oxygen. We know that such high surface productivity, along with its lack of ventilation to the northern part, makes Arabian Sea to suffocate in the subsurface layers. So what happens is that we have a well oxygenated surface layer, but in the mesopelagic region, which is like in the subsurface layers of Arabian Sea, we have very strong or intense suboxic layer. This spans from around 150 meter to 1,500 meters. So it imparts a lot of stress to the local ecosystem there. So, and apart from that, this also has major implications to the west coast of India. In the previous talk, we saw that there is a seasonal hypoxia, which is forming along the west coast of India. That is mainly coming because of the coastal offshore interaction. So I'm not missing out this image, which has been shown in many of the previous talks. So this is just to show you that Arabian Sea is very intense OMC that is comparable to the two major OMCs in the tropical Pacific. Now, having given the brief introduction, we have enough motivation to look at this basin, how it is going to respond to the future climate change. So some of the earlier studies have already shown the importance of monsoon in affecting both the source and sink terms for the formation of this OMC. Given climate change scenario, there has been some reports which show significant changes in both monsoonal circulation, mainly the weakening of atmospheric circulation, as well as the productivity. So we know that there is a huge impact which is coming from the stratification. So stratification reduces the productivity, which in turn reduces the demand of oxygen, whereas the source is also weakened because of the weakening in the monsoonal circulation. So there is a very complex interaction which can make the future prediction very much difficult. Apart from this difficulty, we also have some limitations, which is, again, which has already been discussed in many of the earlier talks. We have very poor representation of this OMC in the global climate models. So I have shown here 3 CMIP-5 present-day simulations validated against the observations, which is from World Ocean Atlas Climatology. So what I show here is the average of oxygen over 200 to 700 meters. In the left most, we have the observation and 3 simulations under CMIP-5. So I have just chosen these 3 simulations basically because they 3 have completely different degree of present day biases. So if you look closely, you can see that the MPI is very close to the observations, whereas GFDL and IPSL are completely off. In fact, GFDL captures some pattern of low oxygen condition, whereas IPSL is highly oxygenated. It has no oxygen deficient zone. So there is a very recent study which is published in the last year by Henrik Schmidt and the co-authors. They explain and discuss about various controlling factors that causes this kind of present day biases. But also I want to highlight the fact that these models do have a completely different dynamical and biogeochemical component, which can be a reason. Along with that, they also have a very different horizontal and vertical resolution. Now, I will convince you why we have to have a downscaling approach. So in my study, what we did is that I chose a regional configuration of ROMs coupled with NPCD. So this has been used in several studies by Zuhair Lashkar, and it has proven its skill in reproducing the Arabian Sea OMC and various biogeochemical cycles. So what I did is that I performed a set of downscaling experiments. So basically 2 approaches. So one, we have a ROMS control, which is the reference simulation where I force the ROMS with observation in both the surface and lateral boundaries. And then we have a set of downscaling simulations, which I call ROMS historical and ROMS RCP 8.5. So these 2 correspond to CMIP historical and CMIP RCP 8.5. So as you can see details, the surface and boundary forcings are taken from CMIP CMIP parent simulation. So this is performed for 3 models, which I showed in the initial slide. So there is also another approach, which is adding the anomalies to the observation. So this is the delta approach, which has been done in some of the earlier studies. So here we compute the CMIP5 anomaly by subtracting last 20 years averaged for future and the present. So this anomaly is added to the observation to construct a climate change, surface forcing, and lateral boundary conditions. So by doing this exercise, we believe that maybe we will get rid of some of the biases, because the biases in present day and the future are almost similar. So this anomaly will get rid of those biases. Now, having this such kind of downscaled experiment, we have 2 advantages, main advantages, I would say. One is that we use same model for all the experiments, unlike for the CMIP5. So we have both physical and biogeochemical components same, and same horizontal and vertical resolutions. And apart from that, we can do some sensitivity experiment. I'm sure I don't have to explain this much, but in my study, what we did is that we want to understand how much the southern boundary or eastern boundary is controlling the OMC changes in Arabian Sea. So for that, we did an experiment, which I call here as ROMS no boundary. So here the lateral boundary is kept same as in the reference experiment, and we force only the atmosphere with the climate change forcing field. So comparison of this with the control experiment will give how much impact is coming from the boundary. So now getting into the result. So first I will just show you a quantitative validation, again to show how bad are these CMIP5 simulations in the mean state, and how good is my ROMS control experiment. So this is a bar plot which shows the volume fractions of 2 thresholds. One is for the oxygen, when the water with oxygen content less than 60 micromole per liter. So this basically includes both hypoxic and suboxic waters. So that's what we call the OMC volume fraction. And other one is just focusing only on the core of the OMC, where we considered the water which has oxygen concentration less than 4 micromole per liter. So you can see that when we look at the OMC bars, well, we have most of the, at least 2 of the CMIP5 reproducing the OMC, but when it comes to IPSL, we don't have such oxygen deficient zone. But when we focus on the lowest or the core of the OMC, we can see that out of 3, 2 of them do not even represent such high or intense oxygen deficient zone. So this is the case in many of the available simulations. As I mentioned, I picked up only 3 out of all available. So coming to the main result, this is a comparison which shows the projected response of subsurface oxygen. So here again, I averaged the oxygen content over 200 to 700 meters. The leftmost column is for the CMIP5 3 models, and the other 2 are for my 2 different approaches in the downscaling with ROMS. So first of all, we can notice there are a lot of similarities between all of them, and there is also a huge differences. So first, let us focus on the similarities. So basically, we have this positive, this reddish color that is very consistent amongst the CMIP5 models and also among the different model simulations. So we have a very robust oxygenation in the southern part of the Arabian Sea. I forgot to mention. So I overlay the suboxic and hypoxic zone from its corresponding present day simulations over all of them. So you can just see in which region there is a huge difference. So as I mentioned, there is a robust oxygenation in the southern part of the Arabian Sea. So I will be showing the results, what controls this oxygenation. So to understand this in detail, we have decomposed the total oxygen changes into thermal and non-thermal component. So that is the apparent oxygen utilization changes. That's what is plotted here. Again, CMIP5 versus the ROMS downscaling approaches. So you can see that they are very consistent. First of all, the oxygenation is very consistent in this southern Arabian Sea box. which is from equator to the north. As earlier, like in Bob at 2017, we also see that the apparent oxygen controls most of this. And then comes our sensitivity experiment, where we wanted to understand how much is the ventilation or transport that controls these changes. So here I show the comparison of oxygen changes over 200 to 700 meters for CMIP5 and ROMS, two different downscaling approach against the one where I put off the boundary effect. So we can see that indeed there is a positive anomaly, but the magnitude or amplitude of this oxygenation has become much weaker when there is no boundary. So this clearly indicates the role of southern boundary. Now, let me just go to the Northern Arabian Sea. So this is one important point I wanted to make. So this is a profile changes averaged over the sea from CMIP5 and two different approaches. So you can see that there is a huge difference when we look from the surface, subsurface or deeper layers of Arabian Sea in Northern Arabian Sea. So we have a huge deoxygenation in the GFDL as I showed in the map. And in IPSL and MPI, this is completely different throughout the layer. And now another point is that when we use a ROMS experiment, when we use a ROMS downscaling experiment and compute the projection, we see indeed a deoxygenation, which is very huge in the GFDL, but the layer of deoxygenation has slightly shifted towards the upper layer compared to the CMIP. So this clearly indicates the sensitivity, the dangerous aspect which we may end up in interpreting by looking at the climate coupled models. So we have to be very careful in looking at different layers which we try to say oxygenation or deoxygenation is happening in these kind of layers. So when we looked at the bias corrected approach, surprisingly, we saw a very consistent pattern. So we have a deoxygenation, but that is restricted really to the upper 200 meters. And into the deeper layers, we see a big oxygenation. So this is completely different from the other two set of simulation. Other point I want to make here is that the MPI, which is least biased, even if we do a bias correction or without bias correction, we see very similar result. Of course, it is because it is the least biased and we don't gain much by doing the delta approach. So again, this is again the similar, we do a decomposition and we see that apparent oxygen utilization is the one which controls such changes even in the Northern Arabian Sea. So to give a summary, we see robust changes in the Southern Arabian Sea. There is an oxygenation which can possibly cause a shrinking of Arabian Sea oxygen minimum zone in the future. And in the Northern Arabian Sea, the projections are highly sensitive to the present day bias. So one has to be really cautious while interpreting such results. And the main driving factors are mainly coming from the ventilation related changes rather than the solubility factors. So this is expected at the subsurface layers. And in the Southern Arabian Sea, most of the oxygenation is coming from the remote processes that controls the southern boundary of the Arabian Sea. So I thank the organizers of this colloquium once again, and I also thank New York University in Abu Dhabi for funding my travel, along with my co-authors who constantly supported me to complete this work. Thank you. Thank you, Anson.
Thank you very much, Parvati. Great presentation. We have time for one quick question. Sorry.
Hi, thanks for the great talk. I found your profiles of the CMIP models and your downscaling very interesting. Do you have any intuition, or have you looked into what's driving that discrepancy in the depth of change?
Okay, so I have a figure here which I did not show in the main thing. So so when you look at the these are just vertical sections of oxygen at 65 east from 3 different CMIP-5 models, which I was showing. So if you look at GFDL, we have a huge mixing, which is causing such kind of well-oxygenated water that reaches to the subsurface layer. So a reduction of this mixing in the future, or RCP85, causes such kind of huge deoxygenation. So this is very different when we go for ROMs, because we have a well-stratified layer in the ROMs. So we don't see such kind of mixing in ROMs. So that's what brings the difference. Sorry?
Sorry, like you're saying vertical processes rather than horizontal?
Yeah.
Cool.
So we have to be careful what sort of, so another thing is that you see such kind of deoxygenation, but it is not really affecting the OMC because there is no OMC in the GFDL. So we have to really look at the vertical structure of the oxygen and
okay,
thanks.
So that's, we continue over the coffee break later. Of course, the questions about the coastal seas, how they affect it. And now we move on to the to South Africa, and Grant Pitcher is going to present what is going on in terms of deoxygenation or oxygen change there.
Okay. Okay. So thank you. I'm going to change scales here to a sort of base scale and talk a little bit about impacts of aquaculture on local oxygen depletion in the bay pictured here, Saldanha Bay. Now, many of you will be aware that the contribution of aquaculture production to global fisheries production is approaching that of capture fisheries. So we are dealing with a major sector that is bound to have an impact. And it's also known that aquaculture has, in many instances, been seen to impact the environment adversely, and in some cases, in fact, has been associated with complete habitat destruction. Conversely, the culture of extractive filter feeding bivalves has been perceived to provide an ecosystem service in the assimilation of excess nutrients often derived from human activities. And, but nevertheless, when you introduce a very large densities of filter feeding bivalves to any habitat, this has the potential to impact negatively in terms of water quality. And this may include localized oxygen depletion as a consequence simply of organic loading of the system. And I have a little video here which just profiles a raft culture system of mussels. And I've put it in here just to introduce the sheer biomass that is introduced into the system with culture. And you can see these are ropes. This is a single raft. You can get up to 600 or 800 ropes on a raft. And they provide habitat not only for, or substrate, not only for the mussels. See, there's tons of biofouling material as well, which is often dumped during the harvesting processes into the bay. Then you can see this massive organic matter below the rafts and above the sediments. And then when you get down to the sediments themselves, you can see these white mats or bacterial mats. So yeah, there you can see them properly. Okay. So now our study, which essentially is a monitoring program, simply sets out to assess changes in Saldanha Bay in response to the establishment by government of a so-called aquaculture development zone. Now, Saldanha Bay is located on the west coast of South Africa and is therefore linked to the Southern Benguela upwelling system, but also feeds Longabon Lagoon down here, which is a shallow tidal system and also a declared Ramsar site. Now, the ADZ is simply intended to expedite expansion of farming operations within the bay. And it in fact sets out nearly 900 hectares for the farming of mostly shellfish farming, usually, mostly mussels, but also oysters. Now here we see the ADZ, the Aquaculture Development Zone, indicated by these grayed out areas. So they look in 5 discrete areas. Now the bay itself is divided into this, what they've referred to as outer bay, but also this inner bay region. And the inner bay was divided in the 1970s by the construction of a causeway for iron ore terminal. And this created 2 sectors, with different hydrographic regimes, simply named Small Bay and Big Bay. Now to date, 90% of the aquaculture has in fact been undertaken in Small Bay. So I think we can assume that any impacts we see would in fact be limited to this area. Now, oxygen has been included as well as several ecological indicators for monitoring the impacts of aquaculture on the bay. And included in this monitoring program are these quarterly synoptic surveys of oxygen profiles at these 27 stations. And they're intended to cover all regions of the bay, both on-farm and off-farm. And then I should point out this station 1 out here is considered representative, essentially, of the coastal environment. Now, synoptic surveys have provided the opportunity to look at temperature-oxygen relationships, which are quite useful in operating systems. And we looked at these relationships in different regions of the bay. And these are the relationships from our 9 profiles at Station 1, which, as I said, is representative of the coastal environment. And we can see a pretty linear relationship, although there is an apparent change in the relationship with season. Now, of course, any deviations from this relationship would be informative in reflecting the effects of either the bay or the other impacts, such as aquaculture. And here we take a look at the plot of temperature versus oxygen from all stations during a single synoptic survey. This was conducted in July 21, and this shows considerable deviation from this linear relationship. In the outer bay region, we still see that linear relationship, but when we move into the bay, we see that it deviates substantially. And specifically in the areas of the intensely farmed areas, as indicated by the gray and pink dots over there. So essentially, the areas and these areas have lower oxygen concentrations than we'd expect with that particular temperature. And we see exactly the same pattern if we look at the relationship of temperature and pH. So we have lower pHs in the intensely farmed areas. A further difference in the oxygen regime between Big Bay, where we have very little aquaculture, and Small Bay is prevalent or evident in these profiles of so-called what we're referring to as oxygen debt, which is simply determined as the difference between the measured concentration and the oxygen solubility value. And recognizing the great variability we see, it is evident that the oxygen debt in the surface waters tends to be greater in the more intensely farmed areas of Small Bay. And this is very likely simply to be attributable to the lower phytoplankton biomass which we're seeing within the Small Bay. And this is either owing to the hydrodynamics of the Small Bay, or in fact could well be to the lower the high shellfish feeding rates in the bay and the lower primary production as a consequence. But ultimately, whatever the causes, the lower production in Small Bay will in fact eventually affect shellfish production. Now, additional components of our monitoring program is the deployment of these bottom mooring of 4 instruments, again, on and off the farmed areas within Small Bay and Big Bay. You must note that they are, of course, deployed at different depths, but they're essentially on the bottom, or half a meter off the bottom. And here you can see the oxygen time series we get from these, moorings. These are the two time series from the Big Bay area, both the control site and the on-farm site. And we can clearly see seasonality in the oxygen time series. Bottom waters are clearly ventilated in winter, and then oxygen tends to decline through summer and reaches the lowest values, ultimately hypoxic conditions, essentially in late autumn. As you can see, superimposed on seasonality is strong variability at the event scale. The time series between the two are very similar, and this we believe is simply with the fact that there's very little shellfish production in the Big Bay area. And we do see that hypoxic conditions are present essentially at 13% of the time at both mooring sites. So if we move then to Small Bay, where all the aquaculture production is, we see a notable increase in hypoxia, from 13% in the Big Bay area to 22% in the Small Bay area. But we also see that the lowest concentration of oxygen are observed in the intensely farmed areas of Small Bay. And this approaches anoxic conditions on several occasions. Now, we also see that the variability on the farm site is highest. And this is simply a function of the shallow water in which the shellfishes are farmed, only about 7 or 8 meters. And so this results in regular ventilation. And it's for this reason that hypoxia is in fact evident less often. We're down to 16%. But what we do see that within the farmed area, there's an increase in severe hypoxia, which we arbitrarily determine as less than 0.35 milliliters per liter. Just narrowing down on a portion of that time series, this is a 5-week period from just the other day. And this time series of temperature shows this clear event scale variability of 6 to 10 days, which is something you find in upwelling systems. And it's a function simply of coastal upwelling. And what's happening very simply is that under conditions of coastal upwelling, this wedge of cold water is driven into the bay, and that causes surface waters to be driven out of the bay. The reverse happens under downwelling, of course, that this bottom water retracts from the bay and it essentially draws water in from the coast. But ultimately, and also there's turbulent mixing will also affect the depth of the thermocline. But in the end, it's the vertical displacement of this thermocline that dictates the observed changes in the bottom water temperatures within the bay. And we similarly see this controls events of bottom deoxygenation and ventilation within the inner bay, specifically in Small Bay, where all the aquaculture is. And again, we see the same thing with pH. So if we go back to our temperature-oxygen relationships, what we see in Big Bay is that the lowest oxygen concentrations are confined to a very narrow temperature range, and they occur essentially during late summer and autumn. Moving to the relationships between Small Bay, we see that in Small Bay, low oxygen waters are much more prevalent, specifically in the farmed areas where near anoxic conditions are found, but they also importantly span a greater temperature range of about 4 degrees. And so, to conclude, what are we able to conclude? I think the first thing is that Saldanha Bay is susceptible to low oxygen, and that hypoxic bottom waters are present throughout the entire bay at times, specifically in autumn. I think we can see that hypoxic conditions are more prevalent in Small Bay. This, of course, could be attributed to the iron ore terminal, which was constructed in the 1970s and is likely to have contributed to reduced or increased residence times within the bay. But within Small Bay, we see severe hypoxia is 2.5 times more common in the ADZ of intense shellfish farming. And this is very much likely a function. And of course, that's despite the fact that these waters are regularly ventilated. And these observations are a function, we believe, of the rapid drawdown of oxygen as a consequence of elevated organic farming. And these results, I think, alone would suggest that farming production should be capped in a small bay. But what, of course, we would like now is the development of a model which will be able to quantify the different drivers of deoxygenation in Saldanha Bay. And this would also provide us with a predictive capability to better manage the bay in terms of the growth of aquaculture. Thank you.
Thanks a lot, Grant. It's a quick question. Yes. Natalia.
Yeah, thanks very much. I was just wondering, is there any evidence that this higher regime of hypoxia prevalence in Small Bay has any negative impact on the aquaculture, the farm species themselves?
No, we're not really looking at the impacts on aquaculture itself. We have seen direct impacts on the bentha communities, but they, in fact, do tend to be limited to pretty close to the mussel rafts themselves, but nothing on the aquaculture itself so far. But of course, this is, we're not talking about a massive production here. I mean, there's been low production in the bay for some time, but we're talking about 1,000 or 2,000 tons. But in the last 2 years, it's grown up to about 8,000 tons now and continuing to grow quite rapidly because of this ADZ establishment. So, you know, if it's not allowed to grow uncontrolled, it's going to have bigger and bigger impacts.
Great, thanks a lot, Grant, for this aquaculture impact and also management talk. Now we switch scales again, and Esther Portela will give us the global, go back to the global picture, I think. And you changed your title, great. Okay.
Edit.
So.
Is it okay? I have a pointer. Oh. Thank you. Thank you. So, hello everyone. So I changed a bit the presentation. I'm sorry. I'm going to be talking more about the physical mechanisms driving ocean oxygen uptake and less about transport, but I hope it's going to be interesting. So, well, the motivation of this study, I am not saying nothing new about it. So the ocean is losing oxygen over the past decades, and it's also the oxygenation is predicted to increase in the next century. So this oxygen loss has been attributed to ocean warming through different mechanisms. So acting more directly through a decreasing of oxygen solubility, and more in a more indirect way through, for example, the increase of respiration rates and the increase of ocean stratification, which all of those have a direct impact by decreasing oxygen concentration and also by decreasing the ventilation rates. And that results in a decrease in oxygen uptake and oxygen transport. So in this talk, I'm going to focus on the mechanisms driving the oxygen uptake and release by the ocean, by the interior ocean. So we are going back to the mechanistic understanding of these processes. So the method I used to address this question was to compute oxygen subduction as the flux of oxygen from the mixed layer into the ocean interior. So this is composed by two main terms, which will be the kinematic term and the diffusive one. The kinematic term is composed by lateral induction, eddy-induced velocity, and vertical velocity that you can see here, schematized here. So it's basically the velocity crossing a mixed layer gradients, and this vertical term is mainly Ekman pumping. And then we have this diffusive term, which is all, computed by the horizontal and vertical components. And well, I will give more insight on that just next. And to do this, we use the physical components from ECHO, ocean state, and the oxygen concentration is from World Ocean Atlas. So it's going to be a mean state. So I'm talking first about this diffusive oxygen subduction. So I'm showing two maps in the top panel. We have the vertical component, which we compute. The diffusivity coefficient was computed from internet tides. So we have to say that it's a lower bound, but in contrast, it has a nice, more realistic spatial distribution. And then the lateral component was computed with a constant value of that diffusivity, but to test the sensitivity of this computation and the potential of contribution for the total oxygen uptake, we computed also an upper and lower bound. So here I'm showing you in the top panels the kinematic components of oxygen subduction. So we can see that, well, in the bottom panel, we have the total oxygen subduction. So we can see that this is the lateral induction term, is the one that is shaping the global oxygen subduction. We can see a strong positive and negative hotspots of oxygen uptake and release by the global ocean. But we have that in the global integral, this is some term that is releasing oxygen. Then we have this eddy-induced term. I put a question mark because honestly it's a very complicated term to compute. We use the bolus velocity from the ECHO. And the most we can say about it is that it's patchy and it reflects the eddy field in the ocean. And then we have the vertical velocity term, which is generally weak, but it is homogeneously constant and homogeneously positive in the subtropical gyres. So when we do the global integral, it results that is the main term that contributes to the total oxygen subduction. Or it looks like that. So now if we add the diffusive terms, we can see that's also weak. But I am giving some numbers here. So with our computation, with the terms we chose, sorry, we could compute that this is accounts for 21% of the total oxygen subduction. And with the lower and the upper bound, it ranges from 10 to 64%. So we can see that this is a term that's, I'm sorry, is absolutely not negligible. And indeed, it can be quite important and is absolutely necessary to get more better estimations on this term. Last thing we did with this study was to try to assess the role of the mud waters formation on the oxygen uptake. So I'm showing this map from Thales of the mud waters in the ocean, and we did analysis by density layers and basins. So these gray bars are the oxygen uptake in each basin, and the green bars on top are the oxygen uptaken by the mud waters. So in the surface with the outcropping isopignos correspond to mud waters. So we can see that this is quite big. And what we learn from this is that it's as big as 70% of the global oxygen. So 70% of the global oxygen uptake occurs during mud water formation, but they occupy only 35% of the outcropping surface in the ocean. So it's also very important to very, very well resolve the mud waters in models. For example, we want to really estimate the oxygen subduction. Also, we learned that different subduction mechanisms dominate in different regions. So we have these tropical gyres with a strong vertical velocity, and then hotspots in the North Atlantic and Southern Ocean with lateral induction. And that oxygen diffusion is locally small, but it likely plays a key role for the global integral that need to be more disentangled. So now that I gave the overview of oxygen subduction, I'm going to focus on a case of study in a very important region of oxygen uptake and ocean ventilation in general, which is the North Atlantic, and particularly the Irminger Sea here. So I'm focusing on the ventilation of the Labrador seawater, which is a mud water formed by winter deep convection, either locally in the Irminger Sea or also advected there from the Labrador Sea, which is also formed. This water mass, for this reason, is a key water mass for climate by transferring tracers and signals to the ocean interior directly. And then it's going to be transporting depth over the Atlantic basin and the ocean. So what we did was to gather an extensive oxygen database. We looked for all the data we could find in this region. You can see here the data. So we have hydrographic sections, repeat hydrographic sections across this line, and then also Argo data. So we covered the period 1991 to 2018, and the Argo provide more resolution on the 2010-2018. We define this Labrador seawater by a thickness, layer thickness analysis, so not fixed isopycnals. Because it's a mud water, we can identify it by thickness or relative vorticity. So we have here we see the variation of the thickness and isopycnals in both the hydrographic sections and the Argo data. So we see that is varies in thickness, so in stratification, depth, and isopycnal layer. So kind of different signals. And finally, we perform this separation, this decomposition of oxygen concentration to try to assess the role of solubility, like oxygen, how much oxygen this layer can take by oxygen concentration and saturation, and the apparent oxygen utilization, which is given mainly by biological consumption and mixing between water masses between different oxygen concentrations. So I'm showing you here more quickly these sections. So this is typical the sections of hydrographic from hydrographic repeated shape sections. So we have salinity, temperature, oxygen, and AOU. This Labrador seawater is the one between the thick lines. We can see that with the data, we have long-term variability because it goes from 1991 to 2018, but low resolution. So not all years are covered. We have some gaps here, but we still see the variability of this layer. And then this is the Argo data. So over this period, highlight here with a square. And here we have a shorter time series, but we have a strong, very high temporal resolution. We can identify seasonal cycles and even the injection of events of oxygen here, for example. We can link it with temperature and salinity conditions. And we see in this picture that over the past years from 2015, we have a strong oxygenation and changes in properties of the Labrador seawater. So now I'm focusing more in the Labrador seawater layer. So this is an average over the layer, combining the Argo and the hydrographic sections. So in the black dots and lines are oxygen, the observed oxygen, and the red dots and lines are the oxygen at saturation, but it's offset by a factor of 7%, which is more or less the average of undersaturation due to deep convection in these regions. So it's just for plotting purposes, and I will discuss that later. So the first thing that we can see is that we have no significant trend over the almost 30 years of the record. This is mainly dominated by internal to decadal variability, and that the variability of the oxygen concentration is explained in only less than 1/3 by changes in solubility, and most of it is explained by AOU-related processes like mixing and advection and probably consumption by biology. This is because actually the oxygen saturation changes in a range of about 6 micromole per kilogram, while AOU processes and oxygen vary by even 40. So we did this computation with a variance analysis, and we found that numbers. So now we want to get more insight about what is driving those changes. So we perform some computations using proxies for the gyre, the intensity of the subpolar gyre represented here. So more intense gyre implies different deeper convection, and is going to change oxygen uptake, and with some atmospheric indicators. So I'm showing you here these correspondences. We have, well, the oxygen time series, and then panel A. Panel A is the mixed layer depth and temperature. Panel B is the North Atlantic oscillation, and then there's our proxies of the gyre intensity. So we see that in period 1 and period 3, where the oxygen was high, is near to saturation, convection is deep, we have colder waters, positive NAO, and the gyre is more intense. In period 2 is the opposite. We have less convection, warmer waters, and more stratified gyre, and NAO was negative, and the winds were weaker, and the winds were weaker, and waters were warmer. So we found that relations, And as a summary and conclusion, we have that this red period, so P1 and P3 in the beginning and the end of the time series, this deep convection and high oxygen concentration was, during this period, the AOU was explained by the vertical mixing. So it's within this 7% that we offset from oxygen saturation. And during shallow convection periods, where we have low oxygen concentration, the AOU was mainly explained by horizontal advection, so transport from the Labrador Sea. So our very long time series provided the knowledge about this recent abrupt oxygenation in the Omega Sea. And we saw that there is a lack of linear trend over the past 30 years, and that the strong internal to decadal variability is dominated by changes in AOU-related processes like mixing and advection so far. So that's all. I just thank my collaborators in LOPS in France, and well, those are the references for the study.
Great, excellent. Thanks a lot, Estela.
Yeah, thanks for the call. We should definitely talk after.
Yeah, I'm sure.
I have two questions, if I can. First of all, in your kinematic approach, did you consider the change of the mixer layer depth?
No, there are different ways to compute subduction. So I didn't say that, but the one I chose is Eulerian 1 first, because you can do Lagrangian 2. And also we chose the deepest mixed layer. So we are computing always the deepest mixed layer. Actually, it's a mean state, but we chose the deepest one. For example, in the talk from Benedict yesterday, he used a different approach. But there is discussion on what is better. But
and the second one, I'll ask you later then.
Yes, in the coffee break, you are welcome.
The coffee break.
Go ahead.
If I can ask. Yeah. Do you think with the diffusivity, the diffusion terms that you used, because you can calculate also the formation with this thermodynamic approach using the buoyancy fluxes, and that is not considering the diffusion, this value is missing. Do you think how much would be underestimating then the formation if you don't have the diffusion?
I don't know, but something that we can do, for example, with combining both approaches. I guess diffusion is very important, and it's the term that depends the most on, for example, if we account for changes, it will be important for changes in oxygen subduction, because in the mean state, oxygen subduction is dominated by mass subduction. So you can change the oxygen, but it's not very important for the global picture. But in the kinematic part, but the diffusive part depends a lot of oxygen, or changes in oxygen concentration. So I guess that is going to be quite important, but it's very complicated to accurate estimate. For example, our approach is from tidal internal tides. Those are important at the bottom and mainly dominate in the water column, but in the base of the mixed layer, probably and likely there are other turbulent processes that are important, and I still don't know how to take into account. So any idea on that is very welcome.
Very important. Okay, thanks a lot. Thanks to all the speakers and all the audience for questions. And we now continue with ventilation aspects and impacts on oxygen changes, and have another focus on the Baltic Sea, which we know that's our Baltic Sea index already. So it's one Baltic Sea. And Peter Holtermann is giving the presentation. And Peter, the floor is yours. I try to give you a warning after 2 minutes before the end. I'm not.
Okay, thank you. Yeah, thanks everybody, and thanks for the opportunity to give to have our results here presented at this very nice conference. And we talk about the Baltic Sea and about the advection for the transport of oxygen into the Baltic Sea. And I want to show you one of our major instruments already here on the first slide, which is an underwater winch. And because we tend to always show our nice polished results, I thought it's maybe instructive to show that science can be tedious and not everything goes well all the time. So this here is a turbulence microstructure profile, which is the most corroded instruments according to Rockland. So we, just to give you an idea that not everything is always going pretty well. And as a second thing, I would like to advertise our companion talk by Ole Pinner this afternoon. he will talk about turbulence mixing in a stratified marine system. And I think it's no spoiler if I say that the Baltic Sea as well. Okay, so let's start with the Baltic Sea. And it's just one Baltic Sea, not many. And I really like that the Baltic Sea is taken as, let's say, a volume people can imagine in terms of anoxic water mass. That was not always the case. So if you look at this paper from Carstensen, you see that in the beginning of the last century, there was basically no anoxic zones, and it increased over the time. And we're gonna look at the aspects of turbulent and advective transport on this anoxic situation. Okay, for that, I would like to give you a brief overview about the Baltic Sea. So we are now in the middle, in the central Baltic Sea here, where the island of Dodland is located. And if you make some sort of a comic sketch of the Baltic Sea, then you have a basin is separated into an anoxic deep water and an oxic surface water. So if you go there with a CTD profile, you see in October a situation like this. So you have in red the temperature, which is creating a thermocline, and here, which is causing stratification, right? So because of that, I draw this thin black line here. At the same time, you have the halocline here, which is much stronger in terms of stratification. And for that reason, I draw this very thick black line here. If you look at oxygen, we have well-oxygenated water at the top, and we have zero oxygen in the bottom. But in between, we have this funny amount of little oxygen existing in this depth range here, just below the halocline. And we call it the suboxic zone. And you can basically find it in almost every CTD profile with a good oxygen sensor. And we're gonna talk about the reasons for this suboxic oxygen, let's call it suboxic zone. Okay, to boil problem a little bit down, we can state that in the Baltic Sea, we have oxygen at the top. We don't have oxygen at the bottom, so there's an oxygen demand. And the only thing to get the oxygen downwards is to transport it. And this is either by turbulent mixing or by advection. So you take a water mass with oxygen and you transport it below the halocline and you dump it there, basically. Okay. So we're gonna look at these processes with our goddess. I already showed a little bit in the beginning. So that is our underwater sampling system, which consists of a winch, which kind of lets loose to get this device going up and down. And that is measuring CTD, oxygen, and sometimes also turbulence if we mount it on the system, which is a little bit more of a work. Okay, and I will now show you a couple of profiles or deployments of the goddess here. So that is 4 deployments taken between 2010 and 2013. And there's many more I can tell you, but I don't want to show you all the profiles because it's simply too much. And we stared at it for years and tried to understand what is going on. And I want to make it a little bit faster now and just to focus on the first deployment, deployment 2, and we'll zoom in now to that. Okay, let's do that. Ah, yeah, here we are. Okay, so you see on the left-hand side the temperature of the deployment, the oxygen in the middle, and the turbidity of the water at the bottom. And what we did is we took an average of the whole deployment and calculated the deviations of the average, which you can see here on the right-hand side. Here on the upper panel for the temperature, so blue means deviation towards lower temperatures. And you can nicely see that you have below the halocline, which is an 80 meters depth, you have a lot of these cold intrusions here. And these cold intrusions are kind of accompanied by oxygen, what you can see here. So it's red, so that means more oxygen compared to the average, or turbidity, which you can see here. So that is basically always a combination of these intrusions. And that basically means that we have different water masses below the halocline with more oxygen, and they transport oxygen. And because they are here, there's no way that they have been vertically mixed. Otherwise, there would have been some sort of a smooth profile. So that must have been due to advection. Okay, now if we take all our profiles and make a statistic out of that, then we can kind of count how many intrusions we see in our Goodland basin. And you see here the oxic intrusions for 3 deployments on the right-hand side. And here's a percentage. So up to 20% of the casts we see are, let's say, full of oxic intrusions between this depth interval here. Then they decay, which makes sense, right? And below the anoxic turbid intrusions kind of start here. And it really differs between the deployments. So there's no general trend in that, not a seasonal nor anything we could kind of discover. But what we can state is that there's always intrusions entering our basin, or almost always. Our Goddess deployment is very nice, but unfortunately, it is not a long-term time series over decades. And we backed this lack of data up with our monitoring data to kind of look how active the intrusions have been over many, many years, basically. And this I try to show you in this figure here. So what you see is the temperature and the oxygen at a certain isopycnal, which is directly within this hypoxic zone. So it's at around 100 meters. And let's go to the oxygen first. The first thing is we have a longer time series, but before 28, we don't show data because our old oxygen sensors basically became blind when they touched hydrogen sulfide. So that makes it impossible to detect intrusions. So, and with the, let's say, new SBE 43, that problem was solved, and we deployed them in, I think, 2007 or so. And from that onwards, we can use our data. Okay, and what you see is, so this is micromoles. It's not a lot of oxygen, but it's more than 0. It wiggles around a lot over many, many years, all the time. And then there's a funny period between 2011 and 2012 where there's no wiggling, but an almost linear trend towards 0. Then it's basically 0 over almost a whole year, and then it comes back and wiggles around again. And our interpretation of this data is that during this period here, there have been basically no intrusions into the basin, which is on the first glance a little bit boring, but it is very cool to make a budget. We have seen a lot of budgets already, and I'm going to show you another one here. The thing with our budget is it's pretty open. So the Baltic Sea is not closed in the depth we are looking at. So you have a lot of different transport terms in and out of our budget, which makes it pretty complicated. And if you write it down, so this is our control volume basically. So you have the sediment, you have an upper surface, and we look at isopycnal surfaces basically, and we have a lateral boundary. And if you look at that, so the change of oxygen is by advection through the lateral boundaries, by vertical fluxes through the isopycnals, by mixing. The same for the downside of the area, and then the sedimentary consumption and the interior consumption. And by arguing that this period is so boring here, we can actually get rid of a lot of these terms, and we boil that down to only 3 of them. Yeah, so the oxygen decay rate, which is of that range here, 0.11 to 0.18 millimoles per cubic meters per day, is basically governed by sedimentary consumption and by interior consumption. And if we for a moment neglect interior consumption, we can kind of get the sedimentary consumption and get a range which is fitting actually really nicely with chamber measurements done in the Goodland Basin. And that, together with the fact that intubation of the interior is complicated, such that we could never measure a real decay of oxygen with our limited methods, we suggest that the sedimentary consumption is by far the most significant consumption in the Goodland Basin. But nevertheless, the interior consumption can have a role, and if somebody is experienced with incubations at low oxygen levels with very small rates, I would be happy to discuss with you about that, because it would be a nice information gain for our system to get that number and not to get it with a budget. Okay, that was already my talk. And so I will conclude with, why don't we have a hypoxic transition zone? So the first is we have a halocline, right? So there's not a lot of transport through it. I think that's textbook knowledge. Then we have not a lot of turbulence. And Ole will talk more about this. So it's not zero, but it's low. Then we have intrusions existing all the time in this basin, and they apparently bring a lot of oxygen. We could make a budget, and we can show that the intrusions are actually importing a significant amount of oxygen into our suboxy zone, exactly enough to have it at 20 micromoles on average all the time. Okay, and then the last point is that sediment is a major oxygen sink. And I think that is in contrast to the talk of Subhadeep, I hope I spelled it right, the talk on Wednesday where the interior consumption was more important. So which I think is also very interesting. Thank you very much.
Right. Thanks very much, Peter. Also very good talk, well organized on time as well. Questions or answers to the incubation challenge?
Very good talk, thank you. Is there any evidence that there are photosynthetic bacteria in the Baltic that could produce oxygen at depth in the dark?
Oh, that is a tough question. I don't know, to be honest. I will ask our colleagues who might have more information about that.
Yeah, thanks. I think there was a talk by Testa yesterday at a depth in Chesapeake Bay that there was some production of oxygen at depth. So maybe it's
okay. Yeah, that would be interesting, at least, if that would happen. Yeah.
And I have a question about the shuttles that you have, the just chemical shuttles, manganese and so on. Could they play a role at that depth as well, or are they just playing a role in the oxycline?
Yeah, they play. I think they play more role at the redox cline. Yeah, exactly, at the oxycline. But in the suboxic zone, I'm not so certain if they play a big role there.
Okay, thank you very much. Also for the good acronym GODDESS, and we still, I think these are important issues that stick and that help us, and like the Baltic Volume Index, many things like these really stimulate thinking and yeah, keeping this, moving this forward on the agenda.
Okay, thank you everyone for your patience. I'd like to welcome all of you for the Interactions with Media panel. My name is Jody Rummer. For those of you who might not have met me already, I gave a keynote on Monday, which I was really honored to do. And I was crying, literally crying about climate change and sharks and the lack of research that we have about them. And then I was also quite honored to be a panelist yesterday when we discussed diversity and inclusion and equity in the STEM sciences. So today we're going to be talking a little bit about some of the big questions that I've had over the past few days this week at the colloquium about science communication. And so I'm really honored that we do have 3 panelists with us today. But just a few things before we get started. We did send out a survey, and it was on the Padlet as well, to sort of ask some questions from those of you attending, from those that are attending from abroad online, some of the questions that you might have about communicating and communicating your science beyond the journal article. So we hope you had a chance to maybe survey, but we also have the Slido app that you can download. So if you do have questions, all you have to enter is GO2. Yeah, it'll take you to our platform where a couple questions. You can vote for your favorite question. which ones are really popular, or you can enter in your own as well if there's a question that you want to ask. And that's particularly important for those that are attending this panel from abroad online. So this event is meant to explore the importance of science communication. And as I mentioned earlier, beyond the journal article, why should scientists connect with the media? What are the best strategies to do so? Topics of climate change, which some of us are working with. The aim is to inform, encourage, empower, and guide us scientists to lift our public profiles and let the media help us do that. So by definition, the media is our main form of communication. Traditionally, this is covering newspapers, magazines, radio. Let's see, I'll click here. Here we go. Online, magazines, those types of things. So some of these traditional forms of media. And these are the tools that connect us as humans, us as scientists across the world. There are also lots of different types of media in terms of breaking news, really long forms and features, and even deeper dive investigations. And we're going to get into a few of those types of media a little bit in today's panel. Every day, the media is working 24 hours a day, 7 days a week to cover what happens all around the world. And even in our own backyards. So it can be very local and very global. But how we as scientists get our own voice into that coverage, that's the question that we have. And especially every day, the headlines are covering maybe sports, academics, of course, celebrity gossip. How does our science make it into what's news? So we're going to talk a little bit about what makes news as well. So a little bit about my personal background. I'm coming from the science perspective, obviously. I got into a little bit more of the education side of things. Really honored and lucky to win the L'Oreal UNESCO Women in Science. And that came with media training. And that was one of the first opportunities I personally had to give a little bit more of a voice and face to the science that I do. I found that that was really important. Some of the conversations yesterday in terms of my capacity as a role model. And then, of course, I guess thirdly, because I work with climate change and some of these really big issues that our planet is facing, it was important for me to get those messages out there, to translate that science to the general public. I feel like science is for everyone. Taxpayers are paying for our science in other cases. And so I feel like it's really important that everyone has accessibility to the science that we produce. Just lost my screen here. So I've also found a lot of benefits from communicating my science and doing media stories about my science. It's given not only me it's helped me engage. It's helped me be a better communicator. It's also put my name associated with the type of research that I do. It's given me a lot of public influence, especially if it's policy. Now, back in Australia, where I'm coming from, we are going through a federal election right now, and some of the big issues are climate change. And so it's very important for me that that voice gets out there. It also gives me an opportunity to correct misinformation as well, and be regarded as a trusted expert to the media. So I would like to take the opportunity now to start introducing our amazing panelists. And I guess kind of coming from just a lot of the questions that I've had over the past week about how to use the media. And we're really lucky that we, I think, have just such an ideal suite of amazing talent to be able to speak with us with the panel today. Skilled in very different areas of the media. And between all of us, all four of us, we hope that we can some information and some understanding in terms of how this whole process works, lift our own media profiles, and help us have a little bit more confidence in the way that we're communicating. And this, of course, goes beyond academia and through this media exposure. So I would first like to introduce our online panelists, Jessica Camille Aguirre, and she's a writer who focuses on climate change and extremes. She writes in-depth articles for the New York Times, Vanity Fair, Harper's Magazine, the New York Review, and many others. She's currently a Knight Science Journalism Fellow at MIT, and she's joining us from the US. So thank you so much, Jessica, for joining us. Our second panelist is Elsa Kudek. And Elsa is an editor who has a science background. She is currently the senior science and tech editor at The Conversation in France. And she was previously an editor for the Nature Publishing House, including Nature Communications and Nature Energy. And then our third panelist is someone I've known for quite a long time. Melissa Lin is a communications specialist. She connects scientists with media and other public audiences, and her approach focuses on building trusted relationships with and between researchers and stakeholders and media professionals. I've known Melissa for about 10 years now because she was our comms and media communications officer for the Center of Excellence for Coral Reef Studies, where I'm based at James Cook University. And so I'm really quite honored to have such three remarkable professionals to join us today. And so what I would like to do is I'd like to sit with our team here, and we were going to have a bit of a conversation. But the first question that I have is kind of following on from some of my personal experience in interacting with the media. And I want to pass this to Melissa, because as sort of that interface between scientists like myself and many of you here in the audience and our journalists, Melissa, as a communications officer, has that role. And in the poll, in the survey that many of you took, most people did not know who their communications officers were at their institutions. And if you did, you maybe only communicated them once or twice per year. And so I would like to ask Melissa, can you talk a little bit about more of institutional and media connections and how that works?
Okay, is this working?
Yes.
Yeah. Okay. So yeah, and this is my personal perspective as well from Australia and working with the universities there. So yeah, I'm not sure how that translates across all of Europe and the US, but so a lot of universities in Australia have a dedicated communications and media team that sit within a university, but they have to serve all the faculties, schools, everybody. Sorry? You can't hear me. Can you hear me now? Oh, so close. Oh, thank you. I'm not used to being on this side of the microphone, which is part of a communicator's role. So, so where communications officers sit is between academics and the media, and they're there to look after, I guess, the people at the university. So when new research comes out, when there's something interesting to say, they have the connections and the know-how of the media landscape to be able to connect the academics and the researchers to the right people to be able to promote their messages. So yeah, so I worked with Jody at the Coral Reef Research Centre doing that for a while, and now I sit within a few other different university departments because I work as a consultant, so I freelance and work across a few different areas.
The importance of being able to connect with that interface person, whatever maybe their title is at your particular university or institution.
Usually each university or institution, you can actually find that through the homepage. There'll be a press room page or there'll be a news page. And if you click through, you'll be able to find who your press officer or media officer is. Sometimes research centres that sit within universities have their own dedicated comms person, as we did at the Coral Reef Research Centre, because trying to get your messages out through a big university that has to serve everybody can be difficult. So there are people who have their own specialist communications officers at research centres as well. Sometimes they're not good at reaching out to the people they're meant to be looking after, but you probably can find details online.
Maybe I should add that the communications officer are often in charge of building the website. So they'll put up the news, deal with the events that researchers attend, and also write the press release that will be sent to journalists. So they will gather all the information, text, multimedia, pictures that you give them and push them forward.
Really, really great points. Often as that interface or that intermediate, I know Melissa has been really pivotal in helping us write in a really accessible way as well, getting out of our heads in that scientific jargon and communicating in a way that's accessible to our audience and to our stakeholders. So my next question, I'd like to ask maybe Jessica, so you're not just our head on the screen for a little while there, but can you talk to us a little bit about the different types of media and maybe narrative versus news and the types of media that you work with and how that process pans out?
Yeah, so I think that understanding how to interact with the media is highly dependent on what kind of media you're interacting with. And so I work primarily in magazines and narrative features, but that's not necessarily the case for most journalists. And in fact, I think that statistically, most scientists probably interact largely with breaking news journalists or features writers who are writing for online, which is also something that I do. But just to Melissa's point, I think that especially for breaking news journalists, comms people at universities really act as a guide for them, often really tight deadlines and trying to get information within a lot of pressure. And so they might not have the time to sift through all of the research on a certain topic, but they do need someone who can speak to a breaking news event on their deadline. And so reach out to the comms person and say, I'd really like an expert on this. Can you point me in the right direction? And that comms person will be, pivotal in finding the right person for them who can speak to what exactly it is that they're looking for. So, I think that understanding how to interact with the media, again, depending on what kind of journalist you're interacting with. Breaking news reporters, for example, are primarily looking to be accurate, to be timely, maybe to get a scoop, something that other journalists don't have. But I think that, and they're also looking for, at the end of the day, for illustrative quotes that can help them, tell a news story quickly and succinctly. And then a lot of features journalists are looking for something a little different. So they're looking for all of those things, accuracy above all, but they're also looking for, personal examples, anecdotes, historical examples. I just wrote a piece for Nautilus magazine about ocean deoxygenation, and I spoke with a few scientists, and we spoke at length about their research. But some of the pieces of our conversation that became most important to me in writing a feature were a couple of examples that they mentioned about historic research vessels and how certain fisher people in certain parts of the world had noticed the effects of deoxygenation before it was widely understood in all scientific circles. So, those were kind of examples that were tossed off in our conversation, and they ended up being really important to my reporting, and I ended up returning to them. So, that's the kind of thing that features writers are looking for, because they want to be able to make a story come alive in the imagination of people who are unfamiliar with the topic, and ideally who are not necessarily prone to read a science article. So I think that in the ideal piece, there's something for a lay audience who may not otherwise read something about science, but who can become engaged through these kind of narrative examples. And then I just wanted to touch on kind of a more rare form as the long form narrative piece, especially for magazines. And this usually means that the writer is looking for all of the things that I just mentioned, as well as access to a scientist, an opportunity to build a relationship, maybe accompany them on fieldwork, and ideally be able to watch them in their work, watch them interacting with colleagues, to be able to really tell a much more in-depth story. And then just one last point, because Jody mentioned it in the very beginning, there is another form of journalism, which is investigative journalism, and that's quite different. The aim of investigative journalism is really accountability and exposing abuses of power. So that's not something that most people come across very often. I'll just say very briefly that if you do wish to blow the whistle on something that you see that's wrong, just keep in mind that if you do reach out to a journalist, you will have to, or you will be asked to show what it is that you're blowing the whistle on, that your word alone will probably not be enough. So things like emails or other things like that. And a journalist can walk you through how to share that kind of information without putting yourself at risk. So the best way to do that is to ask a journalist for an encrypted form of being in contact with them. Signal is a really great way. And then holding any kind of conversations that maybe we want to keep confidential only on the encrypted channels or in person. But again, that's not something that I'm looking across very often.
That's really great. I mean, what I'm gathering from what you're saying, Jessica, is the different forms of media, and there's kind of a timeline there as well. In some cases, there might be a really short ad that could be for radio, TV, could be some long feature pieces, and I'm gathering that your passion is very much that longer feature piece. Jessica had mentioned the other day when we chatted about really enjoying being out in the field or kind of on site with the scientists and seeing how the process actually works when they are collecting their data and asking and answering the questions that they have around their question or around their subject. Elsa, I'd like to ask if you could contribute to what Jessica has added.
Can you hear me? I guess you can, yes. So, yes, just to clarify, I'm an editor, which I do not write articles myself. Unlike Jessica, I'm sort of a midwife. I help people give birth to their own articles. So those people could be researchers. They can also be journalists in some cases. So what do we look for as the media from you scientists? First of all, in terms of people, we look for expertise. We look for the person who knows what they're talking about, right? And I know this is not always the case in the mainstream media, but this really should be the case. So first thing, expertise. Then we look for something we call a good client, which is essentially someone who can speak or write in an accessible manner. And this, you might be born with that gift, but you could also learn to express yourself clearly for a broad audience. Then, as mentioned, depending on the media and depending on the news, actually, there are definitely questions of timelines. So we might be in a rush because we're doing 24/7 job. We might be in a rush to cover the invasion in Beirut, for example, because that's news, that's happening now. We might be in no rush at all because we want to cover biodiversity in the ocean and how that's changing. And obviously in 6 months, it will still be an issue. So timelines. And then in terms of topics, we're looking for different things. And I think that's quite generic. We want a hook because we want the reader to know why they should be interested, or the audience in general, not only reader, obviously. And so we want a sense of relevance. Why is it relevant to them? And that obviously means you need to match your audience. If you're talking broad audience, you have to find a relevance that is as broad as possible, but you might be talking to different subsets of these broader public. So what's at stake for them? Why should they be interested? So that's really the three things I think you need to, if you're trying to get into the media's head, is the right people with the right availability given our time constraints, and thinking about the topic correctly. So what's at stake for the audience?
I think that fits really nicely into a couple of the questions that we had on the Slido app. A couple of them are anonymous, but Fabian mentions that communication with science is essential. However, how much of a, quote, communication burden can we be putting on scientists? Do we need more institutional science communicators? I mean, I would vote definitely having an institutional science communicator, and even in highly prominent departments within an institution, such as in our CoreWeave Studies department, really, really helpful. And it's not for everyone. There are a lot of scientists that I know personally that do not like with media, that aren't really into that, and that's okay. But some are really wanting to explore that avenue, that area of their science, and do better and learn how to more effectively and efficiently communicate their work to a more broad audience. And in that case, there are a lot of training programs, a lot of coaching programs that are available that can actually be supported by your institution. Sometimes it just takes asking. And then the other question relative, do you want to comment?
Yes, just a comment on the communication burden. I do understand that many people just don't feel like that's their main expertise. They're scientists, communicators. Obviously, as you know, with funding processes currently, there is more and more this outreach that you need to. So I would definitely advocate for more communication officers helping scientists do that. But this is definitely a box that people need to check more and more. What we try to do at the conversation is help the scientists express themselves, just helping them do it. So you can check that box.
Melissa, did you want to add to that, Melissa?
Is that better? Yeah, I agree that it's obviously quite essential, because what's the point of science if no one knows about it? It does become a bit of a burden, but it is becoming an essential part of everyone's job. I mean, to get in Australia especially, you need to be able to show that you're having impact, and that includes communication. So it is a big ask, but there are communicators around that can help, if not in your institution. I know in Australia we have a lot of private companies that help groups of people. Training at the conversation to be able to write articles for the conversation. And yeah, I mean, there are different avenues. And at the end of this, we are putting together a tip pack of where you can go to ask for help. So hopefully that will, help ease the burden a bit.
Well, and I mean, training isn't just a one-off either. It's something that you would want to be refreshing your skills on a regular basis. And so, I would highly encourage those of you who are interested in that to seek out that information from your institutions and see if there are training modules or workshops that are available from experts, like people that are sitting next. I do my training at least every year for the climate media that I work with. I train with them probably 4 times per year. And this is something I've been doing for a long time. And so I think that emphasizes that it is a dynamic field with science communication. And how long do you spend when you open up a web page on your phone? How long do you spend on it? And if you're bored, you're gone, right? So it's a very paced world, and it's getting faster as well. Our attention spans are so small. So yeah, so some of those questions on the Slido app really relevant to science communication training and the language that we use. And there are a lot of resources available for that, for sure. Jessica, did you have anything to add with respect to that?
I just want to say that I think I understand that communicating, especially as a scientist who wants to focus on the work, can feel like a burden. But I would just say that so many of the things that scientists are working on are critically important, and that having a broader understanding of the issues can be really transformative to how our planet works. And so I would just encourage scientists who are maybe thinking, do I have to continue to do this? That this is the way that your work can have a broader impact, and I think that's ultimately what science communicators, I don't really call myself that, but science journalists really want to elevate and to act as tools of carrying the message and hopefully catalyzing a certain degree of understanding and maybe even action on some of the issues that are affecting our world.
Yeah, thank you so much. That leads really nicely into kind of what I think about when what might a scientist want, or what scientists may want out of science communication and working with the media. And so over here on the left, this is a list that I put together as a scientist. I might want to raise awareness, and as Jessica had mentioned already as well, I do want to raise awareness of these key issues that the planet is facing, or that sharks or certain organisms, ecosystems are facing in the face of climate change, to encourage action, which could be at the polls for elections, it could be at local and regional policy making, management, to promote myself as an expert in my field. And that's not meant to sound narcissistic or anything like that, but especially as a female rising in my field, it is really important for me to be seen as a role model and an expert in my field, and also to promote my mission and the awareness of what my institution does for research and the types of findings I have, or my organization. But what does the media want? What does the media need? And so I'd like to pass it back over to Elsa and to Melissa and to Jessica. I mean, I made a bit of a list here that they've helped me with. Can we comment on some of these points about maybe what the media needs? Do you want to start?
Is this working? Sorry. What the media needs, we have talked about different kinds of media. So there's breaking news media, there's the the more narrative sort of media, and there's investigative pieces as well. So I think we have kind of covered that. We need talent that's reliable, that responds in a timely manner. But there are things for breaking news called news values that kind of explain the why does this matter to me, for the audience that media outlet is catering for. So I can't remember all of them, but you need something that's, say, breaking news. It could be something that's really quirky. I mean, quirky gets into the news a lot. Something that's really beautiful in photographs or video that captures the imagination and attention of the audience. Oh, there we go. I could have just read through that. Conflict, I mean, that's always is. And I think human interest is really important. So with news values, you need to be able to connect with the audience of why your topic's important and why it's relevant to them. So I always ask, not only what are your main messages when you're trying to do stuff with media, but why it's important and to who, and what the impact is on them, on the economy, on society, the environment. It really has to have kind of that follow through, I think. But I mean, you might be a better place to comment on that.
When Kenny last night says, "So what?" so many times when we were having some conversations, "So what?" And that's a very short way of saying that, but who cares? Why should we care? And then getting a bit of that personal story in there as well. Those of us that are, this next generation and working with climate change, well, why do you care about that? well, I don't want my planet to die, for one. So Elsa, can you comment, please?
Yeah, I was going to bring this. We've been facing a situation where there are so many things going around with opinions and not facts. And so scientists have been trying to set the facts right. And now there are some calls, I think it's Naomi Oreskes who discussed this at length, actually, saying that scientists should actually talk a little bit more perhaps about their own emotions, because that's a hook. So I really appreciated when you mentioned, Jody, about crying in front of sharks. But I think that actually people can relate to that. You know, the facts are obviously super important. The science is the basis of everything. And you know that better than anyone because you're scientists. But to relate to human beings, emotions work quite nicely too. So not every media is made to convey those emotions, and it doesn't need to be the center of your piece, but it can be a little part of it.
Jessica, did you have anything to add, maybe from the personal perspective, given that you do these longer pieces and sometimes you're out, you know, side by side with some of the scientists and seeing sometimes our frustrations and when something doesn't work or when we're let down by something happening or feeling really depressed about our findings, perhaps?
Yeah, I can certainly speak to that. I think that, you know, just to reiterate something that's important to keep in mind when you're thinking about what the media wants is that it's highly dependent on what kind of media you're interacting with. And so understanding who it is that you're speaking to is really helpful in terms of you know, meeting what it is that they're looking for. I would just say that for the kind of work that I do, which is often long-form magazine pieces, I am looking for kind of to go beyond the way that the science is presented via kind of institutional, you know, press releases, for example. And so I am actually looking for those kind of authentic moments of you know, frustration. And I think that can make people nervous because it feels as though, you know, they're you know, failing in the public eye. But I think that what that does is that it allows people to see kind of the process, the way that things happen. And I don't think that any journalist who knows what they're doing won't see a temporary setback or failure as an indication of the scientist's worth, but rather as you know, a moment that really sheds light into how science is done and what happens when you meet a frustration and how you move forward and how you get over that. And so in that sense, it can be, you know, it can be an uncomfortable process, but it can also be, you know, highly rewarding. I also want to return to the question that was asked earlier about the burden of communicating, and I would just add one last point I don't think that we touched on, which is that I also think a lot of scientists are working in areas where they are raising questions that have, you know, profound ethical implications. And so I think that there's a responsibility to also communicate the science that they're working on in order, because you know, those questions are deserving of a broader social debate. And so I would just add that as another good reason to communicate the work that you're doing.
Oh, that's great. And I think that goes to a point that was raised earlier as well, that it is becoming a part of our job. I know in all of the big grants that I'm applying for, that there is a section for impact. How am I connecting with the stakeholders, the groups, the policymakers that need the information that I'm generating from my research, industry, whomever it is? It's really, really important. You know, science needs to get out there. And so definitely that. We did have a really great comment in the Slido app as well that We have an emergency with global warming and need to dramatically change our ways of living. Scientists have to get out now from their neutral posture. So a little bit is getting out of our comfort zones. We scientists, we're used to sort of hanging out in our lab or maybe just doing our field work and talking in our words that we understand and collecting data. But it is really important, those of us that can, to get out and spread the information and provide that evidence base on which decisions are made that are going to ultimately save our planet. So I think it would be really great to have a few questions from the audience if we have any. We've got some really nice questions from the Slido app, which I really appreciate. We do have a question in the back, so we can just break up this a little bit and then we'll go back to our panel.
Hi, good morning. I was thinking about this, and we have, especially in Brazil, and I think in all countries it occurs, what can we do about fake news in science? Because if I make a research and maybe there's another point of view, different, there are divergence, I don't know, but things could be seen in different ways, but fake news are a very important problem in science. So how could the media, the people could act against fake news in science, especially because we have many projects that could be impacted by this fake news? Thank you very much.
Very good question. That's actually a huge topic that many people in the media are trying to tackle. And I think here it might be frustrating for every one of us, but we're just tiny drops in the ocean. Every single action we take is a tiny drop, unfortunately. So in my opinion, you need to speak up, state the facts, state them again, build expertise, get a network of people that assert your expertise, and that will be peers in your case, right? That's how science works. Speak up again and again and again, and find allies in the media world to help you speak up. And it's going to be frustrating.
It's very frustrating. The problem with, I guess, the rise of social media as well in the last few years is that everyone has a voice. It doesn't matter who they are. But the only way you can have a voice in that is by speaking up, as Elsa said, and building your networks and getting encouragement and support from those you work with. I'd like to say also that in the media, we also have, I'm not sure if it works in Europe as well, but we have a lot of fact checking. So the ABC is our national broadcaster in Australia. They run fact checks on whatever claims and things are made in the media and prove them or disprove them. I'm pretty sure The Conversation has something similar where they run fact checks on claims that are made that go wide and spread misinformation. I mean, there's also sites like Snopes. I'm not sure if that covers a lot of science, but there are actions being taken to counter that. But yeah, having your own voice and being part of that conversation really, really helps as well.
I think that I'm taking this opportunity to is something I intended to keep for the last thing, but it's about being proactive and stepping up and if you feel like it, make yourself known to the media. So there are different ways to do that. There are expert registries. So for example, in France, we have Les Experts for women scientists, French-speaking women scientists. Obviously the conversation and obviously social media. I mean, sometimes I feel like Twitter was invented for journalists to get their news. So get out there. You'll find your voice by doing it. So it's okay if you don't have it straight off, because you hold expertise that people need. If you know about learning theory, we learn better something that we've sort of have heard of before. So it's by repeating and getting into people into a more comfortable zone that you will get the knowledge to them. And something else you hold that's super important is this sensitivity, the way you see the world because you were educated with science, with logical thinking. And all these you can give back perhaps. I mean, most of you are paid on public funds anyway, right? And you can be proactive and make yourself known.
Use your communications officers to do that.
That was a really, really great question. And it kind of leads into a couple different ways that us as scientists, we can be direct pitching, or we can, and be really proactive. We can be registering for some of these expert registries that are online. The Australian Science Media Panel is one that we're familiar with, but there are expert websites worldwide, really, Climate Council. So I would encourage you to take a direct and proactive approach with that. But then there is that reactive approach as well. Do we have another question from the audience?
Jody, do you mind if I jump in on this fake news question?
Yes, Jessica, please do.
Okay, great. I think that I think it's really interesting that this the question kind of is phrased around this idea of fake news, which is a term that was invented to discredit traditional media, and so I think that and it's an odd term as well, because we have already language that describes what I think that the term is trying to allude to, which is unfounded rumors, lies, intentional deceptions. And so I think that one thing that it's important to do is call what we're calling by its name. So if something is a lie, then we should call it a lie. And I also think that interestingly, going back to the root of the term, trying to discredit traditional media is often employs professional journalists who have training in ethical standards. They have a process, a means of verifying claims, certain kinds of, like I said, ethical standards that they have to adhere to. And so in that sense, traditional media, in this kind of ecosystem of information that we're all trying to wade our way through, traditional media can often be the place where the most reliable information can be found. And so in that sense, I think that being discerning about who you speak with and the process that they're using to report the story is important. And calling what other information that pops up, calling it what it is, I think is also really important. And then that's something that is everyone's responsibility. Saying that something that is a lie or that's a baseless rumor is a lie or a baseless.
Oh, that's
rumor.
a really great point. And being part of the conversation, we have that opportunity to call something out if it's wrong and to correct misinformation. We're going to take another question from the audience.
Yeah, thank you very much. My question has to do with if you could provide a little bit more clarity on the expectations for scientists, because sometimes I feel like I've run into maybe the wrong expectation about whose story it is. Because right, as a scientist, you spend so much time working on this research. And so then you reach out to the media and it feels like it's your story, but that understanding that it's the journalist's story as well and the communication expert story, and kind of how you navigate these, two strong potential voices and kind of whose story it is in the end, right?
Well, I can start, but my answer won't be the most relevant. So because the media I work with, researchers sign their article, we remain behind the curtain.
So you mean like when you reach out to a journalist with a story, but then they say to you, we'll take your quotes, we'll do the story, you don't get to check it, we publish it as we see. Yeah, that does happen. So that's why it's really important, I think, before you engage with the media, to have all your main messages ready, what you want to talk about. And when they ask you questions, and if it's going in a direction you don't want, you find a way to come back to your main messages, so that you're sometimes always just repeating yourself. So all they can quote is what you're giving them. And then they can build their story around that. Because in the end, it is their story, but the messages will be yours, I think. Hopefully that kind of answers it. It is tricky. It's really tricky. But there are good journalists out there to work with. And sometimes it's a matter of avoiding the bad journalists. And a communications officer can advise you on that. Does that kind of... Yeah.
No, thanks for that. And with training, it does help because we get a little bit more information on how we can, take that ownership and make sure that we can bridge into a topic that we do want to talk about and away from a topic that we don't want to talk about. Another thing that we had on the previous slide was when it comes to photographs and videos, which is often something that journalists and media really want. But, I've had in some cases photographs not being credited. So it just takes a lot of practice to really emphasize to the journalist that, oh, this is my title. I like to be called by this title, and you can use this photo, but only if it's credited. And then you have that conversation. So it comes with a little bit of training. I'd like to start to wrap things up because I do realize that we're running into the next session. And I would like maybe a closing thought from each of our panelists, maybe like the most important phrase or thought that comes out of their background. And then I do want to emphasize that we are putting together a tip sheet with just some helpful resources and bullet points that can guide you into that next step if this is something that you want to pursue, that we'll make that available to all of the delegates of this whole colloquium. So maybe Jessica, online, what would be your catchphrase, your elevator pitch in terms of what you find important and what you would like to communicate to us scientists about that relationship?
Yeah. Well, I think that the first thing that I would like to say is that it can be frustrating or not rewarding to interact with the media, and so I think, all of the journalists I know are deeply grateful for the time that they're given, and so that's something to keep in mind. I would say also that I think that the relationship between a journalist and a scientist can be collaborative. And it can be a conversation. And so, I would just urge scientists who are interacting with the media, to ask questions, ask, how a journalist is approaching their work, or, what it is exactly that they're looking for, who else they'll be speaking with. To understand that it is a conversation. It's not, unless you're doing TV, you're not getting put on a mic and asked to do a quick quote or a clip. It can be much more than that. It can be a collaborative process. So that's something that I would urge you to keep in mind.
Build those relationships with the journalists, with the media, with your media officer. Build those relationships and learn from each other. Melissa, can I have a last comment?
I know communication and the media is probably new to a lot of people. It seems daunting, and it's a whole new way of communicating and being a scientist with other people. But as a communications officer, I'd say make the most out of your institution's communications and media team. And if they're not helpful, hopefully some of the other resources we add to the tip pack can help. There are other organisations and people you can reach out to. And yeah, a lot of journalists really are very helpful and quite kind if you're new to doing media. Some aren't, but yeah, they're pretty obvious, the ones that aren't, I think.
I would say that step up. You can do it. You can find the people who will help you do it. And I think the world needs you, needs your science, but needs your science in a digestible form, not only the data points.
Okay, yeah, no, thank you so much. We're going to wrap things up with this, but please feel free to reach out to us as well. This is meant to be catalyzing a conversation and catalyzing something hopefully in you that will help you to feel more confident and to start to build those tools with your own work to better communicate and get your really important science and messages out there, and to build those relationships with the people that can help you do that. So I would like to thank so much to our panelists, Jessica joining us from the US, Elsa that's joined us today from France, and Melissa that's joined us from Australia. So please join me in giving them a warm round of applause.
So I'm glad to have our second keynote speaker, Boris De Wit from the University of Toulouse, and often also working in Chile. And he will show us brand new results and ideas about the ENSO-induced variability in the Southeastern Pacific OMZ. Boris, the floor is yours.
Thank you, Andreas. Hello, everybody. Thank you to the organizing committee for inviting me. So this is my first in-person meeting since the beginning of the pandemic, so it feels good. Well, still, I have a lot of screen on me, but that's fine. So Andreas mentioned that this was new results. This is actually not new. Some of them are new, some of them are old results. My talk is more about providing material for a discussion, trying to understand which key process we have to consider to interpret oxygen minimum zone variability at intermittent time scales. So I called it ENSO-induced because we know that ENSO will trigger a cascade of processes. So there is not just one process, but maybe there is one that can be considered like the skeleton over which all the other processes can build and produce variability. So as I mentioned, it's a work done in it's a work that gather material done in collaboration with my colleagues. So Yvonne Montes from Peru, she might be connected. Yvan Almandra is a master student from University of Concepcion. Véronique Garçon, that you know. Oscar Pizarro is a professor at University of Concepcion. Aurélien Paulmier and Marcel Ramos from University of Coquimbo. So from the talks this morning, actually I thought the title of my talk could also be trying to understand metrics of the oxygen minimum zone related to ENSO. And one of these metrics is oxygen volume that has been widely used, and Laure Resplendy illustrated this nicely. And we may wonder how the oxygen minimum zone volume may inform in a synthetic manner on the ENSO variability. So my talk will be also about that. And very briefly, the outline. I will have an extended introduction, trying to emphasize the relevance of investigating OMZ ENSO relation, because one of the big motivation besides understanding the impact of ENSO as an extreme event on some aspect of the ecology of the sea. It is also trying to figure out if we can use this information to try to constrain the oxygen minimum zone sensitivity to climate change. So this is a so-called concept of emergent constraint. Can we use ENSO to build an emergent constraint on the oxygen sensitivity to climate change? This is somehow the general framework of this first part. Then I will present some preliminary results illustrating the fundamental role of the wave dynamics, the planetary waves adjustment of the oxygen minimum zone to ENSO. And so in my talk, full disclaimer, I won't be talking about biological processes, and this is not because they are not important, but it's just because I want to, for clarity, I want to focus on one singular process. And I won't talk about some other processes like mesoscale activity, subduction processes, for example, that are also important for understanding oxygen minimum zone variability. And as a take-home message, so I just put this sentence, which may summarize, maybe we'll see that at the end of the presentation, what we could retain from this presentation. Basically, what I want to illustrate is that we have a different duration of the oxygenation event for the oxygen minimum zone of Peru and of Chile, and those of Chile tend to last longer. So we are wondering if the oxygen minimum zone is expanding. So this is I put a question mark to be a little bit provocative. Of course, they are expanding, but it's not clear, as Laure illustrated, where exactly, is it in the core, if it's outside, at which boundaries. So there's still a lot of uncertainties. And this paper from Strama, of course, clearly made that point that the oxygen minimum zone for the offshore ocean in the southeastern Pacific was expanding, at least vertically. But of course, the trend may be regionally dependent. And when we look at the data more to the surface of the oxygen minimum zone, we see that we have some discrepancy with the general idea that oxygen minimum zones are expanding. This is, this figure from the paper at Ito that shows the trend at 100 meters from the observation, and we see that you have some spots like here of central Peru where there is a tendency for oxygenation. And if you look at some other sources of data at the same location, you could also observe the tendency. This is the data from cruise transects by IMARPE from between 95 to 2013. This is the raw data without interpolation. And if you look at the data, you tend to see also a warming oxygenation of the upper oxycline. So it's not clear. We don't have good confidence in how the oxygen minimum zone will expand. And this was illustrated this morning, and I illustrated it again with this figure that shows the evolution of the oxygen minimum zone volume for an ensemble of Earth system model from 75, 76, which shows the evolution. And as we see, the spread is large, and some model predicts increase in volume, some other reduction. The criteria that was used here is a 45 micromole per liter. This is sensitive to this criteria, as we have seen. Here, this evolution is the baseline for that was the volume, the total volume of the mean volume of the period, the last 5 decades, which is shown here, where we also show that the magnitude of the volume is very distinct between the models. The spread is even more important. There is one order of magnitude here between the trend and the total volume. So how could we try to constrain that? How could we can get some confidence in what's going to happen in the oxygen minimum zone in this region? And to look at this a little bit closer, I show you here the trend at 2 depths. One is a 300 meter, and the other one is 100 meter. So just at the level of the oxycline. And here again, a big dispersion, no confidence, but still we have the ensemble mean indicate a positive trend, so oxygenation, and at 100 meter. And the striking aspect of this figure, the one at 100 meter, is that it resembles the pattern of the sensitivity of the oxygen at this depth to ENSO. So what I'm showing here on this side, on the left-hand side, is a gradation between oxygen concentration, anomalies in concentration, and an ENSO index. So I'll be providing more detail about which index I'm using, but basically this is an index for a strong events, so the one that matters the most for this region. And as we see, there is some kind of similarity between the patterns, of course, regional differences, but overall, we have this tongue of more oxygenated waters from the tropics that goes along the coast up to the coast of Chile. And we may wonder at that point if the sensitivity of the oxygen in the OxyClean to ENSO may be an indicator, maybe a predictor of the sensitivity of the oxygen for the long-term mean. So basically, this means establishing an emergent constraint and using what I call the ENSO sensitivity, that is the oriented sensitivity to the ENSO variability as a predictor. So this concept has been used in many studies, mostly for atmospheric and oceanic science. There are plenty of paper on that, and it has been applied just recently for biological variables. So this is something we may want to look at. Here, in the following, I will concentrate on two sections. It's kind of a bit arbitrary, but this is where also we have some data to compare with. And the section at 12 south, here along this black line, and the one at 30 south. And we will look at the similar diagnostics in terms of vertical section. So this is a section at 12 south, 30 south for the ENSO sensitivity. And this is a similar diagnostics for the climate sensitivity, so the long-term trend. We see here again that vertically, we also have similarities between the patterns. And we also see that the ENSO will tend to erode the upper bound of the oxygen minimum zone. And climate change, apparently also from the model, would tend to deepen the oxycline and reduce the oxygen volume from its upper bound. So how these are related, this is something we can try to look at, with the idea that with the conceptual ideas that in a world where you have more extreme ENSO event, you tend to accumulate oxygen anomalies on the long-term trend. So this is a vision from a statistical sense, easy to understand. If you increase the number of events that produce oxygenation, you might result with a residual on the long-term trend. So there is some sense in looking at that. And the motivation also to look at that is that in the ENSO community, it took us about 10 years to confirm that El Nino will indeed increase in frequency and magnitude. This was some kind of methodological issues that was resolved, and we can assert now that El Nino will tend to increase in the future. So this is a recent paper in Nature that shows here the variance of the so-called E index that I will detail later on for a group of models that do reproduce some aspect of El Nino. And we see that we have this increase in variance. So now to look at this concept of emergent constraints, the idea is to relate for each models the sensitivity to ENSO, so the value of this regression coefficient, to the value, the amount, the amplitude of the oxygen change per the degree of warming in the tropics. So we want to relate these two types of sensitivity for each models. And this is what we have done here for 12 south and 30 north. And so where you have on the x-axis the value of the regression coefficient in within the oxycline. And the climate sensitivity here, that means the oxygen change per degree of warming. And this is the points are for the different domain models that we have been using. And we can see that for Peru, you have some kind of regression, but it's quite, it's not that important. But for Chile, we have a significant relationship, meaning that we can maybe use data or other products to constrain the oxygen climate change sensitivity. And here, of course, we know we don't have much data, so this exercise is difficult to do, but still we can try to use some model with more realistic characteristics like the high resolution ones. And as an example, here I have put the values that would provide such a model, regional model. The blue line here is for an in-cast simulation of regional models coupled to the hydrochemistry that provides an estimate of the ENSO sensitivity. And so assuming that the model is realistic, you would get here an estimated value of the OMZ sensitivity. So this is, I'm just recalling here the basic concept of emergent constraint, and to motivate the study of ENSO and its influence on the oxygen minimum variability, knowing that this is just purely statistical, and to get confidence in such a relationship, we need to provide some mechanistic understanding of what's going on. So here I just recall a figure from the paper by Gan Pitcher, which summarize some of the mechanisms we know about and that may be important during ENSO. So basically, you have the equatorial currents, the equatorial system currents that provides oxygen to the system. And actually, equatorial current may not be the most important. You know that you have these narrow currents near the equator, the Chuchilla jets, that are important for feeding the oxygen zone. You have the coastal wave activity. Kelvin wave here can be trapped and modulate thermocline and the oxycline. You have the transports by the Peru, the undercurrent here that is connected to the equatorial current system that also provide a conduit by which OMZ can be modulated. And you have this so-called ventilation, which is a process that gather actually a number of processes. One is a subduction process that was talked about in the morning, which operate actually at very slower timescales than ENSO. So this may not be a dominant process at ENSO timescales, but you have also variability in the South Pacific anticyclone that we modulate the longshore winds and act on the upwelling system. And you have also the process I'll be focusing after is the Rossby wave radiation. At ENSO timescales, the law of physics tells you that the Rossby waves needs to radiate. It cannot be trapped. So you actually don't have trapped waves at ENSO timescales. And this Rossby radiation is actually part of the ventilation of the oxygen minimum zone inside the oxygen minimum zone. And you have also AD's activities. I won't be tackling this topic here. About ENSO. Recently, the ENSO community came out with this word to characterize ENSO. They call it the ENSO complexity. And this refers to the fact that we have different types of ENSO and we have different characteristics. And if I have to summarize what is ENSO complexity, it's basically an asymmetry in three characteristics. An asymmetry in amplitude, the fact that you tend to have El Nino stronger than La Nina. And this is illustrated here. This is anomalies during strong 97 El Nino, and this would be the La Nina in 89. So if you do the difference between both, you come up with this figure, which is a skewness, but you would get the similar figure doing the difference between these anomalies and this one. And you see that and strong El Nino event do change the circulation in the region that interests us, which is the region of the oxygen minimum zone. Another characteristic of the complexity is a difference in pattern. You see that the El Nino is more east, and the La Nina and his brother, the Central Pacific El Nino, is actually more central. So it would impact. It is supposedly impacting less the oxygen minimum zone through wave activity. And the third asymmetry that appears to be important to understand maybe the long-term trend is that El Nino has, there is also an asymmetry in the duration of the event. So El Nino tends to be stronger than La Nina, and La Nina tends to last longer. So this is a picture just summarizing the efficient equatorial collection during a strong El Nino event, where you have the Kelvin waves here that modulate temperature, but also modulate oxygen in Callao here. And this actually is often interpreted as a coastal Kelvin waves, but it is not coastal. This is actually resulting from the radiation of Rossby waves. So basically, if you have this, this is a longitude time evolution of the Kelvin waves, and where you see if you are in south, you would see from the shore a wave that will propagate offshore. And this is kind of a statistical summary of what's going on. You see that this is a typical ENSO cycle where you see you have this radiation of the waves. And the line that I put here is not the limit of the oxygen zone, is actually the time that a wave would take to reach, it is the time that a wave takes in 1 year, because waves actually propagate much faster in the tropics than to the high latitude. And this process is key to understand how the oxygen minimum zone will evolve zonally, meridionally. This is what I will try to illustrate. Another important aspect here is that those waves are not just propagating zonally, but they are also propagating vertically. So this is you have this beams of energy that, while the waves propagating zonally, also go to the deep oceans, and this through advection and mixing could also influence oxygen minimum zone. And the basic conceptual model that could produce such variability is written here. This is a simple advection and diffusion model. So, which metrics for deducing ENSO sensitivity to ENSO? And there's also the idea in my presentation, does model resolution matters? It's not just in terms of AD activities, but also in terms of aspect of the coastal dynamics. And also I want to emphasize on the difference between the sensitivity to ENSO for Peru and Chile pooling system. I use two models. It will illustrate that, a regional one that is supposedly more realistic than the global ones. And I've been using the CSM model because it provides many realization of events, so you have stronger statistics. I won't go on to the validation of the model, but what I want the point I want to make here is that oxygen minimum volume actually capture the seasonal evolution of the radiation of the Rossby waves. I'm showing you the volume for the regional model, and this is the volume for the global models. And here below would be the ENSO index, where you see that during El Nino you tend to have this reduction in volume, that what you would expect. And in one case you don't have much correlation with the ENSO index. Correlation is actually small, maybe stronger for the global model, but still not a strong correlation. But if you, I will. How many time do I'm left now? Oh, okay, so now my point here is to try to demonstrate that this radiation of Rossby waves would influence not only the upper oxygen minimum zone, but also the bottom part. And this would generate phase difference between the change. Here, if you separate the volume into upper part and a bottom part, so the upper part will be blue and the bottom part will be red. First of all, you know that there is a comparable variance in variability, meaning that volume has to do a lot with what's going on at the bottom part of the oxygen zone. And the second point I want to make here, there is some time delay that is not so much apparent here between the upper part and the bottom part. And to look at this more precisely, you could do the lag correlation between ENSO index and the volume for the different type of model. This is regional model, this is total upper and bottom part, and this is for the climate model. And you see that correlation is maximum at 3 lags for the upper part and almost more than 2 seasons for the upper part. So you tend to have this vertical propagation of the signal inside the oxygen zone. So what would that convert into in terms of correlation between the actual oxygen concentration at some sections? This is at 12 south, where you have a lag correlation between the ENSO index and the oxygen, and at different lags. So you can see this evolution. And -6 would be ENSO ahead by 6 months, and 0 would be at the peak phase. So typically in December when El Nino peak. And you see that you not only impact the upper part at the peak phase, but then you tend to develop here what's the signature of the Rossby waves that propagate vertically with a shape that is typical of what would you expect from theory. So this is a zonal, this is a section at 12 south. You can also want to look at that along the coast. So within a fringe of 2-degree range, similar diagnostics, where you would see in that case, the meridional extension of the ENSO signal to the south. And what's striking here is that, of course, Peru system is directly impacted by the Rossby wave activity and the Rossby wave activity, and also the intraseasonal Kelvin wave activity that precedes the ENSO development, where you see here increase in oxygen. And as El Nino develop, you tend to propagate to the south. But the result I want to emphasize here is that while the Peru OMZ has fully collapsed at the peak and ENSO, it tends to recover at the same time when the Chile oxygen ENSO is collapsing. So you have this phase delay between the ENSO impact by 2 seasons. And this has, of course, implication for how long these oxygenation events will last over an ENSO cycle. Unfortunately, I don't have too much time to look in the detail, but we look at that in the climate models. And we actually see that climate models do reproduce this faster transition from El Nino to La Nina for the Peru system. Whereas off Chile, you have this persistence of oxygenations during this type of events. Okay, so my conclusions, which are more like take-home message, sort of say, so there is a delayed meridional adjustment of the oxygen during ENSO, which is with more persistent oxygenation of Chile during strong events. So there is not this sharp reversal to La Nina condition and hypoxic condition like of Peru. So you would expect a stronger residual of the oxygenation event on the long-term trends, which might explain that the emergence trend is more robust for Chile. Then something I haven't tried to go, I haven't succeeded in going to the detail is the interpretation of the evolution of the oxygen volume, but basically oxygen volume capture the spatial impact of the Rossby wave on the oxygen zone. So we have to be careful when we interpret diagnostics based on oxygen volumes. And something I haven't shown, but that we can imagine that there is a large diversity on how models simulate those aspects. And this is primarily due to the representation of the oceanic teleconnection on the coast. Thank you.
Thanks a lot, Boris, for this great insight into the dynamics of these ENSO-induced changes. Time for a brief question.
There's an online question.
Online question. Okay, yes. Please go ahead. Can you?
So it's Aurélien.
Aurélien, please pose your question. Otherwise, we read it out. Can you read it?
Yeah.
Or show it.
So I will read it. So Aurélien is asking if it is possible to determine a mixing coefficient, for instance, a KZ, associated with the mixing due to the Rossby waves from surface to the lower OMZ boundary.
That's a tough question. The dissipation of the Rossby wave in the bottom part of the ocean, so around 1,000 meters, is associated to how well is simulated the vertical structure of the Rossby wave. Because as you move zonally and vertically, you tend to involve variety scale at very fine scale on the vertical, and this of course depends on model resolution and depends also on the energy transfer from the coast. So quantifying this dissipation, it theoretically it would be possible, but in practice, due to limitation in the model formulation, it's not an easy task.
Okay, thank you. Interesting also to see that the signals are propagating southward, and that you don't see any northward signal from the Southern Ocean. But well, that's very exciting. Many things to discuss in the coffee break. We move on here. And the next speaker is Alison. You have to say your last name. Well, we have to remember that's important for citations and all.
It's recognizable. Alison Hogikian. Thanks.
Okay, I will try. And she's looking at climate models and the impacts of getting drier, well, dry getting drier and wet getting wetter, and whether we have to worry about that when we think about oxygen. The floor is yours.
Thanks. Yeah, thanks for having me. And thanks so much to all of the organizers for helping out and your great work. So I'll also be importing some ideas from the climate sensitivity world, as we saw with the multiple models, but thinking about an atmospheric response to global warming and its potential impact on ocean deoxygenation. So first, to motivate and give a hint at where I'm going, we've heard a lot about global deoxygenation, but in fact, there are parts of the global ocean that have been observed to have a trend towards increasing oxygen content. And a recent paper showed that there is a robust increase in oxygen in North Atlantic mode waters. So the solid red here just designates that it's a significant trend. And of course, it's warming, and so temperature trends can't explain this. So what else might we need to consider? Now, a couple fairly recent studies suggested that this dry get drier trend, which I'll come to in a minute, is increasing salinity over North Atlantic mode waters, which is increasing ocean heat uptake significantly. And so something that's increasing mixing and increasing ocean heat uptake, it's logical to wonder if it might also increase oxygenation of those waters. And because it's a pattern, it could also decrease oxygen content elsewhere. This is part of a broader pattern where mean salinity patterns are amplified with warming. And so to orient you, on the left, I have a figure of the mean salinity. You can see the Pacific is fresher than the Atlantic. Subtropical mode waters are saltier than their poleward counterparts. And you can see that this trend is broadly amplified. So where it's red, it's getting saltier. And you can see that's broadly subtropical mode waters. You can see the Atlantic is getting saltier. The Pacific's getting fresher. So on very large spatial scales, the trend reflects the mean. We see this also in depth in the Atlantic Ocean. And so I'm going to be using for this talk the section shown in the black line on the map. And the colored contours in the figure on the right are the mean salinity with depth. And so the green lines are fresher and the brown lines are saltier. Mode waters are saltier than intermediate waters, right? And so where it's red, again, it's getting saltier, and this is reflecting the mean salinity pattern. So this is to orient you again, and I'll come back to this, the structure of this figure. Now, the theory here is that mean patterns of net precipitation and net evaporation are amplified with warming. And so where precipitation exceeds evaporation, we expect atmospheric moisture convergence to increase with warming and as the atmospheric moisture content increases. And this must be balanced by an increased net freshwater flux in these regions that were already wet if we're on land or fresh if we're over the ocean. Similarly, regions where evaporation exceeds precipitation, and so they're dry if we're on land or salty if we're over the ocean, we expect that divergence to increase. And so this has to be balanced by an increased net evaporative flux from the ocean to the atmosphere. And so the phrase that was coined was dry get drier, wet get wetter. And it's been adapted for the ocean to salty get saltier and fresh get fresher. So now we're all caught up with what my title was all about. I'll go into how I'm going to try to understand the effect of this change on oxygen. So I'm using a global Earth system model. And so this has an atmosphere, an ocean, land, chemistry, biology. And if we specify an increase in atmospheric CO2, it produces warming, it produces ocean deoxygenation, which is what I'm showing here. And the black line represents just a fully coupled experiment. Now, this is an idealized scenario where we force the model pretty hard. We increase atmospheric CO2 at 1% per year until it doubles, and then we hold it steady at that level. And the idea with these experiments, which are very common in sort of atmosphere land, is to get a clear signal of global warming. So the numbers here are less significant than the trends and the relative magnitudes. Now, we can also specify other things than CO2. And so we do an accompanying experiment where we don't allow the ocean to see this hydrological cycle amplification, this salty gets saltier pattern. And we do that just by restoring the sea surface salinity towards the pre-industrial climatology. And so while the black line includes all of the climate feedbacks, the blue line includes all of them except the hydrological cycle amplification. And so we're going to approximately represent the effect of this amplification with the difference between these two experiments. So the terminology I'll be using is sort of a total climate feedback, and then the difference between the experiments is representing the hydrological cycle contribution to that climate feedback as a part of the total climate system response. One final terminology point to make, I'll be using this AOU framework that we've seen a few times now, where in my case, a trend in oxygen can be decomposed into the saturated component, which we calculate from temperature and salinity, and the remainder is attributed to something else. So biology or circulation. But for my purposes, since I'm using two of the same, strongly CO2 forced models, I'm gonna, for the purposes of this talk, assume that it's mostly a circulation change. So to get a sense of what the model is doing in space, we're back to our section in the Atlantic, and we see that the total change in oxygen content on top is, overall mostly blue, mostly a decrease in oxygen, but it does reproduce this increase in Atlantic mode water oxygen content, which was found recently in observations. And when we do the decomposition, this is attributed largely to this AOU term, so largely circulation changes. So again, if it's warming and circulation is weakening, why would there be this increase in oxygen in mode waters? must not be just due to temperature alone. And so when we sort of extract the hydrofeedback signal with our model experiment, again, we get the increase in oxygen in mode waters, decrease in North Atlantic deep waters, and to some extent the decrease in Antarctic intermediate waters. And again, it's attributed to this AOU trend. Now, the color bars here are all the same. So this is apparently a really big feedback according to these experiments. And I just want to note that these things aren't intended to add linearly, but it does give us a sense that the hydrological cycle feedback may have a really significant impact on patterns of trends in ocean oxygen. So the figures that I've just shown you are sort of qualitative, and I just want to close by quantifying this effect. So I've split the Atlantic Ocean only into tropical waters, mode waters, intermediate waters, and then primarily North Atlantic deep waters, although there's some bottom water in there. And so if we focus again on the mode waters, which I'm motivated with as the surprising phenomenon, we see exactly what I showed you in the section, which is, so there's an increase in oxygen. It's not due to the thermal component. Instead, it's due to this non-thermal circulation change. And you may be wondering why the effect of thermal is negative, and that's because in the hydrological cycle feedback, and that's because this hydrofeedback increases ocean heat uptake, which is what these other papers showed previously, the 2007 and 2022 paper. And so because the subsurface water is warmer, there's a decrease in saturated oxygen content. That's not critical for this. And then the other really large signal we get, which then dominates the global signal, is the decrease in oxygen content in North Atlantic deep waters. And again, you see the signal here primarily comes from changes in circulation. So the story is really very simple. Where it gets saltier, the surface water is denser and it mixes more. And where it's fresher, you have a stratification of the ocean and it mixes less. So I'll close. I think that took less time than I was expecting it to. And just summarize briefly that if we consider this hydrological cycle effect, changes in salinity, we see that it can explain a lot of the pattern that we see in ocean oxygenation. And it appears so far to be a pretty simple response of changes in surface salinity, stratifying or destratifying their water mass, and then leading to better or worse ventilation of that water mass. Thank you.
Thanks a lot. Thanks very much, Alison. Excellent. And well, I'm completely surprised that
we were too.
Okay, great. Great fun. Questions? Everybody's surprised. Well, one question, you include the Mediterranean here, which that's the context I have heard it mostly, well, in European, the European context, this dry regions getting drier. Do you see any impact of these marginal seas? It's difficult to judge for climate models, but could that matter?
So these are somewhat preliminary results. We haven't specifically quantified the impact of individual marginal seas on the global integral, but I can share, I have somewhere, so the figures that I showed were just for the Atlantic. We see a weaker response in the other basins, which is consistent with the fact that just the change in salinity is much weaker in the other basins. But again, we see that the AOU impact is larger than the saturated impact, and it's overall consistent with the change in surface salinity. So I can't really directly answer the question about the Mediterranean, but generally just the volume. What we've seen in our study of carbon response to this is that actually the volume is too small to have a big impact. So I would guess that that's what would be true for oxygen as well.
But it might affect the Indian Ocean as well. The marginal seas, but again, the climate models are probably not.
Yeah, but again, the response is just a little too heterogeneous and weak to have as big of an impact as it has in the Atlantic.
There's an online question by Taka Ito.
Yeah, I had a quick question. I was wondering if you check the winter mixed layer depths and confirm that it is indeed getting deeper in a subduction area.
Yeah, we so in this North Atlantic mode water region, I don't know, I guess Right, so the winter mixed layer depth, like here, if you can see the cursor, does get deeper. Also in the North Atlantic deep water, it gets shallower. Again, elsewhere in the world, the signal is smaller, but yeah, it does. I'd be happy to chat more about that like later, yeah, and send the data.
Thank you, thanks for the great work.
Thanks.
Okay, great. Thanks you very much, Alison.
Thanks.
And thanks, Taka, also for your yesterday's effort, or the GitHub repository. I looked at it last night, so I think that's a great way to move forward with combining data and models. Good example for everybody to follow. Just a side note. Now we move to an online talk by Ole Pinner. He's at, I think at RV Bremerhaven. And yes, we're talking about boundary mixing. So there was some advertisement earlier by Peter, and we are interested in seeing the Baltic Sea. And Ole, the floor is yours.
Okay, thank you very much. So yeah, I'm talking about boundary mixing in a stratified marine system, and the stratified marine system of question is the Baltic Sea, especially the Gotland Basin, but you have heard that probably from Peter Holtermann before if you saw his talk. So over 3 years, we measured along the eastern side of the Gotland Basin to, in the Baltic Sea is a heavily stratified marginal sea, and everything below 80 meters is basically anoxic, because oxygen gets depleted, but not enough oxygen is transported into the deep waters. And we wanted now to put a number to that fact. So how much vertical oxygen transport is it actually? And for that, I present you now here the results of the 3 years and 3 seasons we covered, namely autumn, winter, and summer. The y-axis is the depth, and on the x-axis is the distance. You see these black lines denote isopycnal lines, and the scattered circles show you the vertical oxygen flux. So red is downward, blue is upward. And you can see directly that we have strong fluxes directly at the basin boundary, but not so much towards the basin interior. And they are also centered around the halocline, this thicker black line. So we have an oxygen transport that is very dependent on the distance to the basin edge. It is also seasonally varying because it depends on wind forcing. So in autumn, where we have strong storms, the heightened oxygen transport exceeds far further into the basin than if we were in the summer, where we have, in general, a lot calmer weather. And one remark maybe also to that is that this mixing is very sporadic. So if you look at the measurement data, you have a few events with a lot of mixing and high transport, and then time spans of not so much, of way less mixing. So the results we have here are averages over multiple measurements. So how did we get these results? We measured turbulence directly, which is maybe one of the most important things here. So here on the picture on the left-hand side, you can see the measured dissipation rate, again for the 3 seasons. And then in the lower picture, the corresponding halocline depth. And you can see a very similar picture to what you saw with the oxygen fluxes. So high dissipation rate towards the basin edge, and then it tapers off towards the basin interior. And also, again, the seasonally dependent behavior. So not so much dissipation in the summer, a lot more in the autumn. These direct measurements of turbulence and also stratification which we need for the calculations were done with these microstructure profiles seen here in this small picture. And combining the dissipation rate epsilon with the stratification, with the description of the stratification n squared, the buoyancy frequency, we can calculate turbulent diffusivity for every profile we measured and for every depth. And then averaging over multiple profiles and over vertical bins, we can combine this turbulent diffusivity with the vertical profile of oxygen and get out our turbulent oxygen flux. But this is only like 1 2D section along the basin, but we wanted to have a more general result. So we extrapolated that to the basin. We divided our results, we divided our basin in 3 regions. So an edge region, intermediate, and interior, all defined by the distance from the halocline to the seafloor. Because as you might remember, the oxygen flux is heavily dependent on that distance. The closer you are to the seafloor, so closer to the basin edge, the higher the fluxes are. And you can see the edge region is quite small. The intermediate region is a little bit bigger. And then the large portion of the basin is what we call the interior. So that means the halocline is more than 40 meters away from the seafloor. And with these, by doing this, we can go from the oxygen fluxes to oxygen transport. So the calculated values are now in these red ellipses. So we have a vertical transport of oxygen of 6 gigamole per year at the direct boundary, and then 10 to 17 gigamole per year in the intermediate region, and then 4 to 5 gigamole per year in the interior. That is an interesting fact, I think, because even though the interior is much larger than the boundary, we have similar orders of magnitude of mixing. So in total, the boundary mixing contributes more than 80% of the total vertical oxygen transport, despite happening in a very small region. Also, with these results, we can now fill in the gaps in the budget. So we compare it with the benthic oxygen demand, which we expect in the 3 different regions. Unfortunately, the budget is still not really closed because turbulence happens, oxygen gets mixed down, but at the same time, this boundary mixing also mixes H2S up, which also creates another oxygen sink, which is not yet accounted for. So unfortunately, at this point, there's still some work to do. And then maybe as a last remark, these results are currently submitted under the same title at the Geophysical Research Letters, and we hope to publish it soon. Thank you very much.
Thanks a lot, Ole. So we look forward to seeing that printed or published. Questions from the audience here? online. Another. I have a question about the generation mechanism. So you don't have tides in the Baltic. Is it wind driven? Is it buoyancy driven? Is it predictable? What do you need to assess the mechanisms?
So the strong dependence on the season leads us to the suspicion that it is wind driven. So strong winds produce internal waves in the halocline, and these will break at the basin boundary, but also siege movements of the, I think it's pronounced sage movements of the in the whole basin create also boundary mixing, because we have a bottom drag or bottom turbulence where the halocline meets the seafloor. So these two mechanisms, I think, are the two most important. So yeah, does this answer your question?
Thanks. And do you have any estimate of whether that's could be more important, tidally driven or forced semi-enclosed seas?
So yeah, as you said, the Baltic Sea has only very small tides up to a few centimeters. But I would estimate that in a tidally driven marginal sea with stronger internal tides, I would expect an even more focus on the boundaries. So the importance of the boundary mixing may even increase further.
Right. Okay, thanks. One more question.
That was a really interesting talk. Thank you. I was just curious as to whether you were thinking of or had already started using a similar approach on other salinity stratified environments like the Arctic, regions which have fairly dense turbulent microstructure measurements, along with other interesting tracer measurements, I guess. So could you produce a similar oxygen transport for Arctic locations, I suppose?
I don't have a good overview of the oxygen measurements in the polar region, but in principle should be possible. So what is needed is for that, of course, the microstructure measurements, but at the same time, a very fast, like a fast oxygen sensor also built on the microstructure profiler. So it isn't enough to do a CTD, measure an oxygen profile, and then do a microstructure profile, because then the turbulence already changed and you don't see these, you will miss or mismatch turbulent patches. So these fast oxygen sensors are a quite new invention. So there probably isn't that much historical data which is possible to do this exact same approach. But with newer measurements, it could also absolutely be possible. I just don't know if they were so interested in oxygen that they put on these fast oxygen sensors on the profiler.
Okay, yeah, thanks a lot. I think that's important to watch out for, and whoever tries to do budgets, but this might be a really relevant term contribution.
Yeah.
Thanks a lot
for the opportunity to give a talk here.
Great, well appreciated here. Thanks. And we move on to the next online presentation by Yassir Edebar at Scripps, and he looks at the potential impacts of atmospheric aerosols. Floor is yours, Yassir.
Okay, can you hear me okay, Andreas? Perfect. And everyone? Wonderful. Hi, everyone. I'm Yassir Edebar from Scripps. And as the title shows, we'll be looking today at the effects of aerosols on ocean oxygen and ocean deoxygenation over the 20th century. This is work supported by computing resources by NCAR and NSF funding. And I want to start with a motivation. There might be a delay here. There you go. The motivation is essentially we want to understand how the oxygen content responded to anthropogenic activities in the 20th century. And that includes both greenhouse gas emissions as well as other anthropogenic activities, including aerosol emissions. This really nice framework by Schlueneger and colleagues decomposes some of the challenges that we see with attribution into observations and model-related problems. With observations, we know that mapping and gap filling and measurement errors can lead to major uncertainties in how much oxygen has changed over the 20th century, as we could see here in this recent paper by Takaito, which shows that a simple change in the interpolation method can lead to, a pretty large difference in the evolution of the oxygen content over the last a few decades. And so we see that the change already has been quite reduced just by using optimal interpolation. Another major source of attribution is natural variability and model response. We know that internal variability in the climate system can mask the anthropogenic trends. And depending on which model we use, that the emergence can differ quite a bit. But still, there's been some work with CMF5 models and large ensemble models that show that for oxygen, emergence is quite delayed over a significant part of the ocean, including the tropical Pacific. And so the focus here today is on a less understood aspect of attribution, which is scenario and forcing of these model simulations. Specifically, externally driven variability, we think of the long-term change in the oxygen content as driven primarily by greenhouse gases, but the radiative forcing is actually a sum of various different components, including aerosol forcings, which are known to play a relatively important role for variables like global mean surface temperature, shown here in a recent paper by Clara Desert. And what the plots to the right show is essentially a simulation without aerosols in blue and a simulation without greenhouse gas forcing in red. And the black line is with all forcing combined. You can see that once you emit aerosols, the warming is slightly stronger. And if you remove greenhouse gases, you know that the global mean surface temperature actually decreases due to aerosol cooling. So we know this stuff really well. But what we don't know is its impact on oxygen. Do we see similar impacts on oxygen, and is it relatively same amplitude? We have a sense that aerosols can really play a big role in the oxygen content and air sea flux from other experiments. This is work I've done with colleagues that shows that, for example, the eruption of Agung, El Chichon, and Pinatubo over the last few decades have led to a relatively large uptake of oxygen during these eruptions. And to the right, you see the global mean temperature with depth and time in the x-axis, and the oxygen anomaly, also globally averaged. And following every eruption, we see that the ocean takes up that oxygen and it gets diffused. And as the ocean is losing oxygen over time, we see that these eruptions lead to a slowdown of ocean deoxygenation, a temporary slowdown. So that really got me thinking about, well, what about aerosol effects on the oceanic oxygen content in kind of a long-term mean, and specifically industrial emissions of aerosols, which constitute a major component of external forcing. And so to do that, I've used the single forcing large ensemble experiment of the community Earth system model. This is developed by Clara Desert and colleagues. This is using CS7 degree with CAN and POP2 coupled to BEC. And it includes aerosols that are not only spatially variable, but also temporally variable. For each different ensemble of simulations, we use, for example, in the first experiment, all forcing combined, another experiment with all by greenhouse gas forcing, and then finally, we remove the effects of aerosols and biomass burning. And to get the effect of those, we simply subtract these different ensemble members from the large ensemble to get the net effect of these effects. And by the way, I'm not showing the geochemical effects, which has been highlighted by Taka Ito. So this is purely climate aerosol effects only. And so the results are not surprising in a sense that aerosols would lead to oxygen uptake, but they're surprising nevertheless. This is the CSM total forcing with the new Ito estimate. And we see that so far that large ensemble change is quite similar to the new revised Ito estimate. So that's encouraging. But what's surprising is that when we take off the effects of aerosols, the effects of greenhouse gases are quite large. So that means without greenhouse gases, without aerosols, the oxygen content would have declined dramatically more. So in one sentence, aerosols would reduce the oxygen loss substantially by about 50%. So that's a surprising part with the magnitude, which is quite different from what we see with global mean surface temperature, for example. We see that the global mean surface temperature is reduced only slightly as a result of the aerosol effects, whereas with the oxygen content, the effect is quite large. So to me, that was really striking. We can look at the effect of these different components by subtracting them from the large ensemble. And we could see in the next slide, the greenhouse effect shown here in red, and the aerosol effect, essentially showing that aerosol lead to significant uptake of oxygen over the 20th century. And we see the sum of the two, which is here shown in dashed line, compared to the all forcing result. And there's a small difference. And that difference might be related to the fact that there are nonlinear interactions between greenhouse gases and aerosols, as well as additional forcings that we haven't considered, like land use change, the ozone change in the troposphere and stratosphere, amongst various other processes. The second interesting result is the spatial patterns. We know from Clara Desert's experiments that the spatial patterns of these aerosol emissions and their impact on aerosol optical depth and essentially shortwave irradiance and the radiative budget in general leads to pronounced spatial patterns in sea surface temperatures. And we can see that also in the oxygen content change. This is oxygen change due to aerosol effect in the panel, in the bottom panel to the center, the effects of greenhouse gases to the right, and more or less the sum of the two to the left. What you note is that the aerosol effects, the spatial pattern of the aerosol effect essentially projects onto the oxygen content of the upper 1,000 meters, with the North Pacific really playing a major role in the global oxygen content loss, in addition to the Southern Ocean and the North Atlantic. There are some negative contributions from aerosols, but these are likely statistically insignificant. And I have not done a significance test yet on these. But it's fairly clear that the major part of the aerosol effect is coming from the North Pacific, high latitudes in general. Also note that there's kind of an interesting similarity between the greenhouse effect and aerosol effect. So that tells us that the ocean might be responding similarly to these radiative perturbations, even though they might be of different signs, specifically in the North Atlantic region. And then finally, when we look, this is kind of a general point that we as a community should think about, which is that the large ensemble mean is the sum of these very large opposing trends in oxygen. So that when we look at the CMAP5 models as the CMAP6 models, and they might be using different scenarios for aerosols and greenhouse gases, we should keep in mind that these are large opposing changes that come out in the model ensemble mean. And then finally, the mechanisms governing this oxygen uptake by aerosols. Here, I'm essentially decomposing the air C-flux of oxygen due to greenhouse gas outgassing, as well as aerosol oxygen uptake. And the dashed line shows the thermal effect. This is essentially what was shown earlier by Allison and others as the AOU versus the solubility component, but from an air C-flux view. And we see that the aerosol effect essentially follows the same mechanism that we see from greenhouse gases, in that about half of the oxygen uptake is driven by thermal fluxes. So that's an interesting phenomena as well, that the aerosols might be leading to changes in circulation or biological consumption at depth. Now, what I showed was purely climate effects on aerosol climate effects on oxygen. This is quite different from, for example, the geochemical or biogeochemical effects of aerosols on the oxygen content. As shown really nicely by Ito and colleague, the deposition of micronutrients might lead to an increase in the oxygen consumption at depth. And so that goes in the opposite direction of the climate effect. So an interesting question moving forward is, what is the net effect when we're considering both the physical and biogeochemical impact? And to do that, we'll have to run new simulations that account some of the impact of the deposition of micronutrients at the surface. And then finally, I want to leave with some other questions, which are, what are aerosol impacts on time of emergence and future deoxygenation trajectory as aerosols are removed? And then what are aerosol impacts on ocean circulation? It seems like oxygen suggests that aerosols might intensify ventilation. And how do other models differ in their aerosol forcing schemes, and how does that project on their long-term mean? And what are nonlinear interactions between greenhouse gases and aerosol forcings? And with that, I'll open it up to questions, and I'll leave my conclusions here in the end.
Right, thank you very much, Yassir. Questions from the audience here? Yes.
Thank you, Yassir. You make the parallel saying that 50% of the aerosols are like modulating about 50% of the signal, and you compare that to SST. But I mean, a better comparison would be the total heat content in the ocean with that, So if you, in those simulation, I was wondering, did you look at the change in heat content between the two? Is it 50% or is it something completely different?
Do you mean the oxygen solubility, the change in the oxygen solubility?
No, in ocean heat content.
I see.
Oxygen to scale more with ocean heat content than SST. Yeah.
Yes, yeah. That's exactly the reason I've used the decomposition and the flux. Also, it was easier on shorter time scale. But I have not looked yet at the change in the ocean heat content, but I would expect it to essentially reflect what we see in the air sea flux. But it definitely on the to-do list, yes.
Hi, thank you. I was wondering, I guess the effect of aerosols is also under radiation, like radiative balance. So do you have an idea why the effect of aerosols and of CO2 is different on oxygen compared to warming? I don't know if my question is clear. Like, why is the effect on oxygen for the two? Yeah.
Oh, I see. I think so. Correct me if I'm understanding your question correctly. The aerosols essentially tend to reflect shortwave irradiance back to space and diffuse sunlight, and so their impact is essentially kind of opposite to the greenhouse effect, but from a shortwave irradiance framework rather than modulating long wave irradiance. And so the aerosols tend to cool the planet and led to cooling of the ocean, essentially a decrease in the ocean heat content. So that's more or less what we expect with aerosols. However, there is a warming component associated with biomass burning, which is included in these aerosol effects. And that's from black carbon and other particulate emissions that tend to also warm the surface. But in this specific case, those tend to reduce the aerosol effects just a little bit. So is that kind of what you're alluding to?
Yeah, thank you.
Okay, thank you very much, Yassir. Just one final, we can move to the next speaker. A comment here, I think we have to be very, very precise. And this last figure, you show the comparison with Tucker's result. I think that was for the upper 1,000 meters, and you show the entire global inventory of oxygen. And the large ensemble has a slower decline than the CMIP 6 runs, as far as I remember. Slightly smaller, 0.2%, which is factor 10 smaller than the other observation estimates. And you're really comparing apples with oranges sometimes here. I think we all do that, and we have to really say what we are doing. And that, with the arrows in this, the agreement is maybe not as good as some curves indicate or suggest, or we want to make suggest it. And I think we need absolute clarity and precision here to disentangle these different data and model artifacts maybe and make progress. Okay, thanks. Now the next speaker is on the stage here already.
I'm trying to keep the time.
Perfect, thanks a lot. So yes, you're chasing me, that's good. Nikolai van Oppen, Bronikowski, and he's at the Labrador Sea, and the floor is yours.
Okay, well, thanks everybody, and I know this is Friday, and I know this is the end of Friday, and I know this is the end of a long week of a lot of information. So I'm going to try and be brief. So I'm the manager for glider operations at Memorial University, which is in Newfoundland, which is kind of at the end of the Labrador Sea. So the Labrador Sea is kind of close to home for me, and I know it's an important topic to oxygen, to global oxygen supply, to the ocean. And I think everybody knows what gliders are, but basically they're these cute torpedoes with wings, and they're just another platform. They collect data, we send them out. Sometimes they stay up as long as 12 months in the ocean, and it's great because for the Labrador Sea, we can just deploy them from shore and they go off and do their thing. And I want to also just acknowledge that I'm very grateful to my colleagues and supervisor, Eleanor and Brad DeYoung, who give me the opportunity to talk to you guys about this stuff. So, and I'm not going to talk too much about the importance of the Labrador Sea. I think this has been covered very well. I think the only thing I want to highlight is that we thought that the interior of the Labrador Sea was where a lot of the export happened, just by that idea that you create a large volume and it flows out. And now we are focusing more on the boundaries. So there's been some studies, and Janis Kuling and Dasha had a paper that recently came out, and there's a paper by McGilchrist et al., Chasing Demons of the North Atlantic, which is also really good, and I recommend to take a look if you're interested. So gliders in the Labrador Sea, we've been doing that for a while. We've been flying gliders into the Labrador Sea as part of different projects. We looked at CO2 together with Dalhousie University as part of the Vitals project, and now we have this Hot Seals Terrific project, which is part of Memorial and NOC, National Oceanography Center. And what you can see here is just two maps. So I grabbed them from oceangns.com, which is a service for glider users. And you see this kind of sea surface salinity, where you have basically a saltier region, a fresher region. These two kind of co-modulate each other, produce this kind of preconditioning phase in here, where you get deep convection in the middle. And you also see these pathways, which are really interesting. So these are depth averaged currents. And these depth average currents circulate around. So it's not just this boundary current that kind of flows around in a gyre state. You also get these pathways that circulate water and mix it back into the boundary. And that's where we think a lot of this export happens. But there is a question about how important small scale features are that transport water in and around. And that is difficult to measure. And so there was a project with Jamie Poulter and Tara Hobart, who was our student, to look at how much eddy and Ekman exchange there is actually between the shelf and the interior, and eddy export is dominating, but that was in the summer. So now we're looking at the winter. And so what we have here is a deployment in 2020. So we had a glider deployed for 5 months in the winter, and the glider observed sort of the large scale pattern that we expect in this region with a deepening mixed layer. We see that water is highly oxygenated in this mixed layer, and below it we see this kind of darker gray layer that then at the end of convection is less dark gray. So it's more oxygen in this deep water, which then can potentially get recirculated into the boundary current and exported. And what we see also is that there's a lot of variability. So we see these small features that stand out. And compared to BGC floats, which are harder to see here, but they're these gray lines, there's strong signals in the glider data. And these are all the BGC floats that were within 50 kilometers of the glider, and we see there's a gap as well. So this glider data is exciting to kind of fill in the gaps. So looking a little bit more at the events before convection, we see that there's several eddies in the data. So this is steric height, just to kind of give us a reference of what the sea surface would be like due to these changes in temperature, salinity. And we see that there's in particular one event where we see pretty strong undersaturation compared to ambient water. So it's like 15% undersaturation. And the question then is, where does it come from? What's the character of this event? Are there many of them? How important are they? So what is the implication? So looking at TS, it's clear or relatively clear that it's not coming directly from Greenland. It's not this Erminger seawater, which is over in this corner. There's a couple different definitions here. One is taken from Piccini et al. And another one just looking at Argo data. And then down here, we have these blue triangles, which is Labrador seawater. And we see that most of these eddies, or these eddies are kind of, especially at depth, they kind of conform to this mixed product. But the or surface signature of lower oxygen water is definitely tending fresher. But we need more context. This isn't very helpful. And so we look at an Argo float that was trapped in the area. It was actually very nice to have a float like this that just kind of got trapped and circulated around these different pathways and captured a lot of this deep mixing. So we see that water mixing in this year actually reached to almost 2 kilometers. And we see that, there's respiration going on in the fall, and then you see some deeper respiration towards the convective period. And so we think that probably some of this low oxygen water is due to these biogenic activities. And if we look at the ETS curve, we also see that some of the scattered points match or overlay a little bit the eddy, and we think that it's happening, that the eddy spun off somewhere from the northern parts of the shelf and kind of entered the Labrador Sea around Hamilton Bank. Looking at the eddy kind of in more detail, which is kind of cool, what you can do with glider data as you zoom in and focus, is we think that on the second pass, so the glider came down, there's some problems here, so we had no data. And the glider kind of came, the second time at least, we think we passed pretty close through the center. And so this is the raw data. We see these, the path of the glider as it's diving up and down, and then we interpolate that and see that we have this pretty defined bolus here. And if we look at steric height, we take the maximum of that and then the edge where you get kind of normal oxygenated water and call that our eddy. It's not perfect, but there isn't a lot of other data to go by. We looked at altimetry and it wasn't really helpful, so we stuck with that, and we think that this eddy was probably around 27 kilometers in diameter, and the velocities at the edges, so these are depth average currents from the glider, were around 20 centimeters a second or more, so not insignificant. So there's still a lot of stratification preserved and energy in this eddy. And so what we do then is we apply the Hatun method, which was for Erminger sea rings, much bigger features. And so our feature is small, But what is astonishing is that there's still quite large drawdown when you scale it by the size of the eddy relative to the Labrador Sea. And the idea basically is that you just take the segment of the eddy that is this low oxygen water, and you assume that you're going to mix it into the Labrador Sea. And that's not a crazy idea, because towards convection, when you have a lot of buoyancy loss, you expect that these features might die and mix into water, which then can recirculate. So that begs the question, how important are these events? Because it's hard to capture them. So what I've tried to do here is I've just tried to identify features in all the BGC floats for those 2 years that had a change in steric height that was an anomaly compared to the seasonal cycle in steric height. And then we looked at events that had this AOU, which was higher than 20, and that were in the same density order as the glider event. So we see that there is events like that. It's hard to classify them. So these are, the colors are months of the year. So kind of group basically into seasons. But it's hard to classify them in terms of, can you really track them? What is pretty clear is that there is a lot of eddies near Greenland. We know that, but this region here is not, like, there should be still more happening is what we think. So, and if we think that we can at least account for 25 eddies like the glider measured, that would be 10% of the export that is mentioned in the paper that I've mentioned a couple of times, the recent paper by Köhling et al. So they could be important. So what's next? So we've had one glider at the time. So now we have 3. And we have one that's south of, that's right around 53 North. So this is a glider that's coming home now. It's actually, this is a screenshot I took just today. And then we have gliders that were further up north in the area that we surveyed before. And these gliders, again, saw a lot of eddies. So there was a lot of features dragging them around up here as well. So we think that we're going to see a lot of these instabilities. And we're hoping that we also capture a little bit of the export coming down. So we hope to see and link these 2 data sets together. So stay tuned for those results. But I'll keep it short, I'll close it. And if you're interested at all, please get in touch. We have a website as well. If you want to fly gliders in the North Atlantic, let us know. And yeah, I'm happy to take any questions or talk about the data. It's all pretty new.
Right. Thanks a lot, Nikolai. Excellent, very impressive. Questions? Yes, please.
Hi, thanks for the talk. I think I need to be guided a bit better in what type of eddy you think it is. Because when I saw the track, I didn't understand if you think it's like a cyclonic, an anticyclonic, a deep eddy, or what it is. Because when you were showing the track, I don't know if you can go back to the slide, but it looked like the glider it crossed it completely twice, right?
So,
but where,
yeah.
where? I mean, I would expect to see twice the same shape, while it looks more like the middle of it is at the edge.
Yeah, I'm
so
cutting it off.
it's very confusing to me.
Yeah, so the full time series looks like this, right? Because we entered it left and then entered again the kind of closer to the center, so you get two zigzags, right? But what I'm showing here is just the part kind of going through the center the second time, because we think it's the better path. But these are anticyclones. Yeah.
Okay, thank you. More questions? Yeah.
When you talk about export, you mean the transport of oxygen from the Labrador Sea to the North Atlantic, right?
Yeah, so the subduction that happens in the boundary current, and
okay.
Yeah.
But then I was wondering, when you look at that profile, I mean, it looks like it's relatively low oxygen compared to the rest. So how do you make your computation of like 10% or of the oxygen transport?
Yeah, so the Hatun method is pretty crude, and you kind of assume that the Labrador Sea is homogeneous in terms of oxygen. So you have kind of a volume of Labrador Sea water that has a certain oxygen concentration. And so you're assuming this parcel of water gets mixed in, like you shake up a glass of water. And so all you can get is kind of relative proportions of mixing one water versus another, and then what the difference would be.
Okay, thanks very much. Nikolai. And we move, yeah, thank you. We move on to the next speaker, Mathilde Jutras. How do you have to pronounce your name as well. We have to remember that. Jutra. From McGill University. We had an excellent post on travel, business travel of scientists, and success doesn't correlate with the number of flights you have. That was my take-home message, very important. Okay, but here I look forward to your presentation on the St. Lawrence estuary.
Okay. Yes, thank you. Yeah, if you have questions about the impact of air travel, you can ask me also. So, yeah, hi, my name is Mathilde Jutras, and I'll be presenting this work that I'm doing for my PhD at McGill University with Carolina Dufour and Alfonso Mucci. So I'll present the causes of oxygen decline in the St. Lawrence area. And you'll see we'll go from local eutrophication, but also to circulation in the North Atlantic. And some of this has been published in a JGR Oceans paper in 2020, and the last bit is a soon to be submitted manuscript. So as you might know, I'm showing the Takahito picture because it shows deoxygenation in the Western North Atlantic and not the other ones. But so the oxygen has been lowering in that area. And on the left, you can see a very dramatic decline in the oxygen concentrations in the St. Lawrence estuary, which is located where you have the yellow star here. And the concentrations went from 130 micromoles per kilo in the 1930s to hypoxic levels about 60 micromole per kilo in recent years. And you can also see the red point is last year, and we actually confirmed this also last winter, and we found much lower oxygen concentrations than in the previous years at less than 40 micromole per kilo. So I'm not going to talk about this data point today, but it will be really interesting to look at it in the upcoming months, and I hope to be able to see what are the causes, but we kind of think it's the same thing that has been going on recently. So here I show this picture. It's from the Claret et al. 2018 paper, and it's a model. You see the color is the oxygen concentration, but I think it shows really well that the oxygen decline in the St. Lawrence estuary is related to circulation in that area, as we see that the Labrador current waters have a much higher oxygen content because they are colder, and they kind of enter in this area. And yeah, I don't have a pointer, but where is and it will affect like the whole slope sea and all the adjacent basins that are found along the way. Okay, so in that sense, it's interesting to study this area because it can kind of be used as a canary in the coal mine of deoxygenation in the Western North Atlantic. So you can think of it in a broader way. And so first I'll show you the decomposition that we did of the different causes of this decline. So first there are some local causes. Here you see the estuary a bit better, and the color shows the oxygen concentration at the depth of the oxygen minimum. And you see it's lowering. So this is an estuary. So we have estuarine circulation, and the water is flowing at depth inland. And as it does, the water is getting lower and lower concentrations with biological activity. And this transit takes 4 to 7 years, and the water is very stratified. So this is a very long time during which eutrophication can happen. This is like a very special estuary, actually. So we don't have seasonal hypoxia. It's like permanent. So we have this first cause. Then we also have an increase in the water temperature that will increase biological activity locally. And then we have these external causes. So basically, we observed in recent years a decline in the amount of Labrador current waters that were entering the system and an increase in the amount of Gulf Stream waters. And this is related to the circulation in that area that is squared there. So basically, it depends if the Labrador current is going to retroflect and turn east and go into the subpolar North Atlantic, or if it's going to come west and enter and feed the slope sea again and the Eastern American continental shelf. So in a second time, we will look at what controls this variability, given that it's so important for oxygen. All right, so to do our budget of the causes, we use observations, and we use this method that has been presented here already, the extended optimum multiparameter analysis. And basically, it's just a linear mixing set of equations for some parental water masses. In our case, we have these Gulf Stream or North Atlantic central waters, and we have the Labrador waters, and we also use the local water mass from the system. And we use 7 variables. They are shown here, for which we had some measurements. We can use, in the extended version, we can use the conservative variables that are conserved upon mixing, like temperature, salinity. But we can also use oxygen and nutrients and things that co-vary according to a fixed ratio. And this is really useful because then we get 2 outputs. We get the fraction of the water mass contributing to the mixing, but we also get an estimate of the oxygen consumption and of the nutrient use between the initial parent water mass location and the location where we make the observation. And here you can see the time series of this proportion or fraction of Labrador and Gulf Stream waters with time in the red square that you see up there, so at the entrance of the channel. And we see that in general, Labrador waters have been going down and Gulf Stream waters have been increasing since the 70s. There was like no trend from 2000 to 2008, but then in 2008, we started to see a very fast decline in the amount of Labrador waters entering this area. And oops, the wrong way. So because of these trends, we will look at the causes for 2 time periods from 1970 to 2000 and then from 2008 onward. And here I show I will show like a budget of the oxygen decline and for the 2 time periods. And this is what we observe at the head of the estuary. So where you have the yellow star again up there. And first we have contribution from eutrophication. Then, as I was saying, the local temperature increase. Then we also have biogeochemical changes that are happening in the Atlantic, so between the parent water mass, initial location, and the entrance of the channel. So this is quite big here, and we haven't looked at that, but this is interesting. And finally, we have this contribution from the fraction of the 2 water mass, so like the amount of Labrador and Gulf Stream water, which is associated to circulation in the Western North Atlantic. And what we see is that in the 2 time periods, the causes, they vary, they are different. In the first period, it's really all these 3 here, the yellow, orange, and green. These are the biogeochemical changes. So they are dominating really the oxygen decline. But in the second period, it's the circulation changes who are driving the change. And so since the circulation is so important, we're gonna explore this a bit more. Sorry, and try to understand what controls this kind of path or the fate of the Labrador current. And if you look in the literature, there are really like 2 opposing views about that. The first one is that what happens with the Labrador waters is due to local interactions between the Labrador current and the Gulf Stream. And the second one is that it's more of a remote control, depends on the Labrador current itself. So to conclude, I showed how in the St. Lawrence estuary, the biogeochemical causes were really leading the deoxygenation until year 2000. And now it's circulation changes in the Western North Atlantic who seem to be driving these changes. And these changes, the circulation changes are important because they influence the whole slope sea area here and the eastern American continental shelf. And they don't affect oxygen, but also salinity export to the subpolar North Atlantic and nutrient concentrations here and temperature. And this has been studied in a couple of studies, like the effect on temperature here. And what we find basically is that this seems to be related to it's controlled, upstream by the Labrador current itself. So yeah, I'll be happy to answer any questions.
Yeah, thanks very much, Matilda. Questions from the audience?
Or if you have comments, don't hesitate to come see me after also. I'll be happy to have comments.
Good. That's a question. Yep.
Thank you for your presentation. It was a really great talk. I wondered if you investigated how the current changes affected the biogeochemical processes. Is it something you've done?
Yeah, okay. So how the current themselves would change the biogeochemical processes here. Well, as you said, there are definitely some changes in the Western North Atlantic, but we haven't studied specifically what they would be due to. Like, we also try to see if there are some trends in the Labrador waters that are carried by the Gulf Stream, if there were some trends in these waters. And there is some variability, but we didn't see any like specific trend or decline in like oxygen concentrations or things like that. So, but yeah.
Okay, thank you. A quick one while the next speaker is coming to the stage.
I was wondering, you showed that the path of the water which is going from the Labrador, this one, which is going basically through the Flemish Pass, but there is also water which is going around the Flemish Pass, and that will mix a lot with the North Atlantic currents, which is going northward, which is a lot saltier. So yes. Have you checked if there's any influence of this mixing with the oxygen?
Yes, well, I think so. I didn't put it there, but it's true. It's quite important. Most of it will come back, but it's like, since it's more the outer part, it will contribute to the part that is exported to the Atlantic more. So I say if it's going east or west, but it's always a fraction of shore, of course. So I think this part is more exported. Yeah, but it still, yeah.
Okay, thank you. Thanks very much. So we move to the last speaker before the coffee break. Giovanni Galli. So we moved back to, or closer to Liège, to Europe, the Western European, Northwest European continental shelf. And look at intra scenario variability. Okay, floor is yours.
Yes, how do I use the pointer? Okay. Good evening, everybody. I'm Giovanni Galli from Plymouth Marine Laboratory in the UK, and this talk is about the evolution of near-bed oxygen in the Northwestern European shelf in a multimodal ensemble. So the Northwestern European shelf is the one that you can see partially depicted there along with its main currents. And I wanted to draw your attention to this current that is entering here from west of Norway. We'll get back to it in the end. It's a pretty dynamic system with a lot of processes going on, including ocean shelf exchange and riverine and Baltic inflows, seasonal stratification and tidal mixing, and is an area that has been known to be subject to deoxygenation events. So oxygen concentration in seawater is the result of multiple processes that can be broadly categorized into three groups. There is temperature and salinity, controlling the solubility of oxygen in seawater. Then there are biological processes like primary production that produces oxygen and respiration that consumes it. And then there is transport, like lateral transport and vertical mixing that move oxygen from one place to the next. And all of these processes pretty much interact in shelf seas and make so that the response can be highly heterogeneous in space and time. Now, Wakelin and colleagues recently proposed a procedure to separate the effects in change in oxygen that are due to change in solubility alone, and that are those physicochemical there, from the change that is due to all other processes combined, that is biology and transport. And I spare you the details, but long story short, it turns out that the change is due to change in solubility alone is proportional to oxygen saturation. And the change that is due to all other processes is proportional to saturation state, that is concentration divided by solubility. So oxygen projections in models are notoriously all over the place, even within the same emission scenario. So to partially address this source of variability, we ran a small three-member ensemble of coupled physics, biogeochemistry, regional models of the Northwestern European shelf using the Nimo-Ersem model suite to the end of the century. And Now, our three models are all the same. What changes are the lateral and atmospheric boundary conditions that were taken from three different Earth system models of the CMIP5 collection that are the GFDL ESM2G, IPSL CM5A AMAR, and AGEM2ES that were chosen because they represent a broad array of climate sensitivity even within the same RCP 8.5 emission scenario. And what I mean by that is what you can see from the pictures here, where we have that GFDL shows the least warming and freshening, AGEM on top shows the most, and IPSL is somewhere in between. And this differential sensitivity is reflected in the change of oxygen that you see here, left column. Well, first of all the models predict a decline in near-bed oxygen throughout the shelf, but the GFDL projects the least deoxygenation, and the other two models project a more pronounced deoxygenation and some notable hotspots of decline along the Norwegian Trench and for AGEM also in the Eastern North Sea. So what happens to saturation concentration? This decreases by proportional to climate sensitivity, but by an amount that is pretty much uniform throughout the basin. What's more interesting is to see what happens to saturation state, right column, where we have the hotspots of decline that I told you about before, Norwegian Trench and Eastern North Sea, but also some areas where the change is actually positive. That's pointing at some mitigating process. So to understand the causes of this variability, we turn at the processes that happen here. And here you see the correlation between warming and between the temperature, atmospheric forcing, and oxygen solubility and oxygen saturation state. And as expected, the correlation between temperature and near bed oxygen solubility is negative and consistent throughout the basin. On the other hand, the correlation between the temperature, atmospheric forcing, and oxygen saturation state is positive and relevant only in shallow and well-mixed areas, especially in the southern North Sea, English Channel, and Irish Sea, pointing at some mitigating effect of biology. And in fact, in the same areas, right column, increasing net primary production correlates positively with the increasing oxygen saturation state. But primary production is a double-edged thing because it does produce oxygen, but also organic matter that settles to the bottom and can be later respired, consuming oxygen. And this is what we see happening, especially in the AGEM model, in the same area where we have the deoxygenation hotspots. We have a negative correlation between decreasing saturation state and increasing near-bed respiration. The same effect is present also in the other two models, but the spatial extent is much more reduced, and it's more of a seasonal thing that tends to happen in the first half of the year. At the same time, those hotspots of oxygen decline that we have seen in the Eastern North Sea and Norwegian Trench also coincide with hotspots of increased stratification, your potential energy anomaly, that is a measure of stratification, that are negatively correlated with decreasing surface salinity and what's that? An oxygen saturation state. And obviously just in the two most sensitive models, not in the other one. So to see what's happening here, we turn at an analysis of the time evolution of change. And here we see that those deoxygenation hotspots developed jointly with a circulation change that limits the exchange between the ocean and the North Sea along its northern boundary. Now what happens here is the time evolution of near-bed oxygen saturation state in blue in the plots closely matching a progressive weakening and reversal of the Western Norwegian trench current. That is that current that I pointed you out in the first slide. That happens happens in the two most sensitive models, but not in the least sensitive one. What happens here is that there is less exchange with the open ocean, so the North Sea fills in with fresher Baltic Sea water. This further increases stratification, and this prevents the transport of oxygen to the deeper layers. So, what have we learned from this exercise? Well, first, that all of our models consistently predict a near bed oxygen decline throughout the shelf, and this decline is proportional to the climate sensitivity of the parent model. Second, that the effect of warming on solubility will decreases the oxygen concentration by uniformly throughout the shelf by an amount that is proportional again to climate sensitivity, while biology and changes in transport are responsible to the more spatially heterogeneous responses. Then third, that decreasing ocean shelf exchange triggers the development of sustained oxygenation hotspots in some areas that are linked to increased stratification. But this happens only in the most climate sensitive models. And lastly, that in shallow and well-mixed areas that are more close to the coast, increasing net primary production can actually be a mitigating factor for deoxygenation. Thank you very much, and I'm happy to answer your questions.
Questions from the audience on the North Sea, or well, European shelf, near bottom oxygen? Yes, over there.
That was a really interesting talk. Great. I was, is that okay? Yeah. I was just wondering, were you running these with some sort of tidal model as well? It's just, as far as I was aware, you know, for example, in the Southern Irish Sea, you have this extremely persistent tidal mixing front that we know is regionally pretty crucial. It mixes all the way to the surface on some occasions. So were you controlling for the effect of tides? I mean, the Channel and the Irish Sea especially, they are pretty crucial.
Yes, the model does include, all the models do include tides, and in fact, in these areas, Channel, Irish Sea, etc., tidal mixing is a very important phenomenon, and in fact, we have a lot of mixing there, and that's why the increasing net primary productivity counterbalances the decrease in oxygen.
Okay. I have a question about feedbacks, biogeochemical feedbacks in the sediment. Do you always find one solution irrespective of your initial conditions? So can you, if you just change the forcing, would your result depend on?
Yeah, we haven't tried changing the initial conditions, so I wouldn't be super sure. You were talking about benthic feedbacks, and yes, and the benthos.
Multiple states that you put it.
The benthos has a bit more slower dynamics, so it could be that a different benthic initial condition does indeed affect the result. I guess it would take a while though for the system to just forget about the initial condition, and also because the benthos is that Nimorsum does have a full benthic model with a lot of equations, modules, etc., but it is quite poorly constrained because we don't have enough observation to calibrate it.
But you haven't found any evidence for that it might switch your results.
We haven't looked into it, but that will be interesting for sure.
Okay, thanks a lot. Thanks all the speakers and the audience for discussing. And good, welcome back to the last part of our journey to Patagonia, where Ivan Perez Santos will lead us to, and looking at fjords and deoxygenation, oxygen changes there, and even link that to equatorial dynamics. The floor is yours.
Okay, thanks again for the conference, for the good conference, and also for the excellent idea to put the best presentation at the ending. So Patagonian fjords are located in the southern hemisphere and also belong to the southern fjord belt. It's a big area with a lot of fjords and channels. Since 20 years ago, the Navy support most of the oceanography study there. I will go fast to present the oceanography background from our study area. And first is the situation of winds. We are it's an area influenced by the westerly winds, that are stronger winds, especially during autumn and winter. And also during the spring season, we have the migration of the Southeast Pacific subtropic anticyclone. And we have a lot of synoptic activity in the area related with wind. Winds is important because wind force the surface current. And for us, the most important now attention is to look at the connection with the equator, and the connection with the equator area is due to the subsurface layers, not by the surface. That connection belongs to is connected with an undercurrent. The name is Peru-Chile undercurrent. She moved from north to south in direction to the polar region. Also, an important feature in the area is the oxygen minimum zone. Even we are in 41 south, we have here we receive the influence from the last part of the oxygen minimum zone. And we need to pay attention. There are a lot of research in that part of Chile and central Chile, but it's very new results that we will present now because we are more south and we also receive the influence of the oxygen minimum zone. Using the World Ocean Atlas information, you can plot and have an idea to the transport at the advection from the Peru-Chile on the current. And look at here, the signal from Sarit for the high salinity that transport that undercurrent. And also important is the transport of low dissolved oxygen and water to this area. I put it on here to make the position of Patagonia, or the door of the Patagonia where the water can come inside. This is the only part along the coast, along the Chilean coast, that water have the opportunity to come inside the area. Of course, Chile is the second country produce salmon, and there are a lot of farming cage, at least around all the coasts on Iceland, and there are a lot of salmon activity, and also salmon, also mussels, algae, aquaculture. Then we are very interested in I show here the study area. We are very interested in that part of, we mentioned this is the Patagonian door. This is the principal area of interchange between oceanic water and fjords waters. As you look, the bathymetry is very complicated, the topography, but the deepest area is here in red color. And outside, as I mentioned before, we have the Peru-Chile on the current between 100 and 200 meter depths. And also here they have this current transporting the water massive, the name the equatorial subsurface water, can throughout to interior Patagonia through these channels. I put here a line in white to mark the trajectory that equatorial subsurface water, the trajectory for the equatorial subsurface water from the outside to inside. And we put just in the middle of the channel, we put that kind of platform. The name is the Ocean Whale Platform because we are in collaboration with a colleague that studying now the migration of blue whale. This is an area, it's an important area of blue whale. Oh, sorry, we don't talk about blue whale, no worry. We continue with the physics. We put in the platform an DCP and CTDO, and this is the information that we show again now. This is the time series. We started the time series in 2016. We now continue the collection of data. And the most wonderful thing was here, look at the oxygen. We have a ventilation during fall and winter, and oxygen go down during spring, and at least during the 5 years, we know now the annual cycle of oxygen. If you look at here, the 2 years, the year 16 and 17 was very high, occurred very high ventilation in the area. We maybe show next what's the problem, or not the problem, the ventilation occurring the causes. But if you took all the 6 years, there are at least a slight decrease in oxygen. Yeah? Even you could these ventilated years. The deoxygenation rate calculated now is 1.11 milliliter per liter years. Look inside the Patagonia now, the distribution of water masses. This is a transect from south to north, and here, in that region, in this area, where we find over the hypoxia, also find the equatorial subsurface water. Then the problem match very well, hypoxia, equatorial with lower oxygen, but there are other processes inside fjords contributing also with the deoxygenation. Sometimes people when look or take some kind of data at the first thing is say maybe it's the aquaculture industry that creates or contribute with the organic matter. But if you look at here, we have now the excellent data from Winkler from 1970, and it's the same panel as we captured last years. It's the same figure with the same features. Then maybe the aquaculture is not the problem there. It's more natural. We have also all the time series, sorry, the cycle will be here. All the time series in sign fields, and here the decrease in oxygen is more stronger. And here the calculation of the oxygenation rate is 0.67 milliliter per liter per year. Unfortunately, we lost the instruments and we could translate it, but we will again repeat the experiment and put all the instrument, all the mooring and there to continue studying this trend of the oxygenation. Of course, also we have the influence of the equatorial subsurface water, but also here we think that the other causes contributing with the decrease in oxygen is the high rate of community in the area, because all Chilean fjords are very productive during the year. To try to understand what happened in the area of interchange, we used the data from Mercator model. It's a nice model for us. We are very happy with the interpretation or result from Mercator. Mercator represent very well the temperature, also the salinity and oxygen feature that we know from the area years before. We also have the possibility to compare Mercator data with in situ data. And result also match very well. Then we continue now with the interpretation of what we are continuing story about the deoxygenation or causes for deoxygenation. Also continue with the validation of Mercator. Here we show now the historic profiles from Winkler from this area that are now included also in the World Ocean Atlas, in the last version of World Ocean Atlas. And when you compare logical, it's very the future of that tongue that we are now very interested in studying the migration, south migration. The Mercator also, the seasonal pattern of Mercator match also very well. We put again the line to mark the position of Patagonia region. Now, using the temperature and salinity, we calculate water masses, and the upper panel showed the horizontal distribution of water masses. Especially, we are very interested, remember, in the equatorial water masses. And if you look at here, we put a triangle to mark the position, and the last part of the equatorial also have the possibility to arrive to that part of the Patagonian doors. Yeah. There's a seasonal map at the level of, we have the bottom in Patagonia. And if you look at down, it's the same image, but in the vertical plane, and we can also detect the arriving the arriving of the equatorial subsurface water to the Patagonian door. Then it's okay and matched with the in situ data, and that's very nice for people that are involved in modeling. If we have now contributing with in situ data to validate models, it's okay. We also use the marine current data from the model to understand the transport, because it's the relation between Peru-Chile and the current with the equatorial is similar or depend on this. And then look at here and the same meridian and transect, we can detect or show distinguish all the transport of the current. And here again is the triangle of marking the position of the Patagonian door. The Peru-Chile and the current is very intense during the fall. And here is the other plane making a cross transect across the transect. We also could distinguish the core of the current. This other panel shows the oxygen, and as you look here, the oxygen from outside can come inside the Patagonia. And at the end, Mercator is a good tool to understand the process that are occurring there. We use this area that's unmarked here to calculate the transport during the time series of the Mercator model. And here, and we were surprising, we are closing now the problem or the understand to what happened with the oxygenation in the last moment or the last years. And Mercator transport of the Peru-Chile on the current means that if we have a transport, we have the possibility that the equatorial subsurface current arrive more and more with blow the water to the Patagonia. That's one of the first conclusions. The second is we have inside the Patagonia, we have the influence of the equatorial, but we have also the organic matter degradation contributing with hypoxia. And the last is the El Niño, a good news for that El Niño ventilate or help to the ventilation in years of 19 and 17. Was a good news, because always when you talk about El Niño, everything is bad. For us, it's good that we have a year with Niño. The oxygenation is okay in Patagonia. Thank you very much.
Thanks a lot, Ivan, for this first or this nice presentation of remote forcing and some effects that could be viewed positive. Questions? Yes.
Done? Yeah. Thanks for a nice talk. So these fjords, they are just so interesting. And I'm just wondering, did you take any sediment samples when you're out there sampling as well?
Yeah, we incorporate, I am a physical oceanographer, but we work together with people from biochemical, from other areas, also phytoplankton, zooplankton. I mean, in order to understand our problem that we have in that difficult area, we need to work together. And we also took sediment samples. But sediment is okay in most of the places. The redox is high because even in the area that we have hypoxia, because sometimes during the year we receive a deep ventilation from the ocean, from water from the ocean during the fall winter. And of course, under the salmon case, we have serious problem with the sediments. But outside, it's no problem in other area.
Great. Okay. Thank you very much.
Thank you. Thank you.
And we move on to Sabine Mecking. She's online, I think. Also looking at remote forcing in outcrop areas affecting the North Pacific.
Yeah. Hi.
Thanks. The floor is Sabine.
Hi. Should I start? It's 7:44 here.
Good.
I'm 1 minute early. Should I start anyway?
Yes, please go ahead. Yeah, we can hear you well.
Anyway, thanks for giving me the opportunity to give this talk remotely. As I said, it's 7:45 in Seattle, but I think it's time for happy hour in Liège. So thank you for everybody sticking around on a Friday afternoon. So as Andrea said, the title of my talk is about the North Pacific. It's about linking northeastern North Pacific oxygen changes to upstream surface outcrop variations. And this is work I've been doing with my colleague Kyla Druska at APL-UW in Washington. And it's funded by the National Science Foundation, which I forgot to put on here. So the motivation for my talk is to better understand the large oxygen variability and the trends that have been observed in the North Pacific thermocline, and they're indicative of ventilation changes, which relates to climate change and decadal variability. And obviously, we think that the ones in the Northeast are related to what's happening upstream where the isopycnals outcrop. And oops, I'm trying to move my, I can't move my, oh, wait, sorry. There's quite a bit of delay. Okay. Anyway, so of course, we're not the first ones to look at oxygen variability in the North Pacific. And to just give a little bit of historic background, I think in 2001, there were like several papers that came out at about the same time reporting pretty large oxygen changes in the North Pacific thermocline, which kind of caught everybody a little bit by surprise because they were on the order of 40 micromoles of kilogram of change between different years, different decades. And there's been many more papers since then. I've been part of some of them. And today, in the a variety of mechanisms have been proposed for these oxygen changes. And today, I just wanted to focus on one of them. So this is oxygen on the right here on one isopycnol, 26,6 in the North Pacific. And this isopycnol is this green line. The outcrop of the isopycnol is this green line, and it outcrops up here in the Northwest. And the blue lines are streamlines. I hope you can see them on the screen, and you can see that water is being transported eastward, and that's how we think changes that are observed in the northeastern North Pacific are linked to the outcropping of this isopycnol. And the lines here are a couple of repeat hydrography lines and the location of Ocean Station P in the northeastern North Pacific. So a question that I've been wondering about for a long time is, do changes in the outcrop location of the densest isopycnals, which 26,6 belongs to, or including complete cessation of outcropping, cause the O2 variations observed downstream? And support for this sort of idea comes from a recent data assimilating model study by Kwon et al. And they put it this way, that when the surface outcrop window expands, the ocean takes in CO2, and when it contracts, it basically doesn't, because we all know that O2 enters the ocean via air-sea gas exchange, and if the isopycnals don't outcrop, then no air-sea gas exchange takes place. So the objectives of the talk is to investigate variability in the northwestern North Pacific isopycnal outcrop areas, in particular in late winter, because that's when the densest isopycnals outcrop, and relate them to the ocean interior O2 variations, and to investigate causes. And that's basically also the outline of my talk. And the data that we use for surface temperature and salinity and subsequently density is the EN4 data set that is provided by the Met Office in the UK. It's a 1 degree gridded product. It comes with 42 vertical levels, but we only use T and S at 5 meters because we're interested in SST and SSS. And it's available monthly from 1900 to the present. We combine this with satellite SST because it provides higher resolution data and provides an extra check of the data set. So we pretty much in the end only look at data from 1982 onward. And I wanted to add Kyla, my collaborator, she's kind of a satellite oceanographer. We also try to use the satellite salinity data that is available now from various missions. And there were a lot of biases in it, and it has recently been combined into one data set called L4 that is QC'd and everything. But in the end, it doesn't tell us much more than EN4 because the data is basically tuned to Argo data, which is also included in EN4. So I put this in parentheses because I'm actually not going to use that. In the interior, we use data from Ocean Station P, which is one of the longest time series in the world, from 1956 to present, and some of the Ghost Ship repeat hydrography section that I've also been part of. So this gives you an idea how outcrop areas vary in the North Pacific. So the colors are density, but what you should be focusing on are these red areas, which is the outcrop area of the densest isopycnal 26.4 to 26.7. And you can see interannual variations. It's very large in 1983 and 2001, these areas, and they're very small in 1996 and 2015. So what this means that there is more ventilation in these years and less ventilation in other years. And some people have described this as the ocean basically taking a breath when the outcrop areas are big and not breathing when the outcrop areas are small. So it's pretty obvious that O2 is being taken up when outcrop areas are large. And on the next slide, I'm going to show the whole time series of outcrop areas and not just these 4 years. So again, these are the 4 plots I just showed. And this is the time series of outcrop area from 1982, pretty much to the present. The red one is using EN4, blue is using EN4 and OS and satellite SST combined. And the differences are actually not come from the different resolution of the data sets. In the end, the data shows the same thing. What they show us is that there are minima in outcrop area. There are basically time periods where the isopycnals almost don't outcrop at all. This here is 1995 and 2015. And in case you can't read the labels, I added the axis here on the left and on the right. So from this, we can see that there is actually large interannual variability in outcrop area, and it looks like a bidecadal cycle maybe with a linear trend on top. So I'm going to compare this to the Ocean Station P data, which is over here. And this is a plot of O2 at Ocean Station P that has in different ways been shown by Whitney et al. In 2007 and others. This is Canadian data. So they published this back in 2007. And this is O2 on several different isopycnals. O2 is the left axis, x-axis is time. And you can see in particular here on this 26.6 isopycnal, you can see these bidecadal cycles that are also observed at Ocean Station P. And to summarize these data, I've made a plot that shows against density, the linear trends that occur at Ocean Station P together with the standard deviation in O2 on each isopycnal. And this plot is maybe a little bit busy, but what you can see is that the trends as well as the variability are largest on the 26.6 isopycnal at Ocean Station P, which kind of supports what we were thinking of in terms of this isopycnal being really important. So again, strongest trends in linear variability on 26.6. So this is great. And I'm going to now show the time series in winter outcrop area together with O2 at OSP. And the magenta and the cyan lines are just the same data filtered. And here we can see the peaks and the minima in outcrop area. And the data from OSP seems to be offset. Like this minimum at O2 could either be leading this minimum in outcrop area or following this one. And so the correlations between the two time series, they show a correlation of O2 relative to outcrop area of about 10 years. It could be either plus or minus 10 years. And we think that a correlation, that O2 lagging the outcrop area actually makes the most sense. The outcrop area changes, it takes the water about 10 years to travel across the Pacific, and then we see the signal of the ocean breathing or not breathing at Ocean Station P. So the correlation is pretty good, so this kind of makes sense. One question we had is, what about the Ghost Ship data, which are the repeat sections? And we've looked at two sections, P16 and P1. I'm not going to say a lot of things about them. I didn't do the whole sections, but just averages. But if you look, for example, at the 26.6 isopycnol, these little circles are the repeat data. It seems like that they're actually leading Ocean Station P on P16 as well as P1 by 2 to 4 years, which is a little bit surprising because they're pretty close by, and we have to look into this a little bit more. So now coming to the causes for the variations in the Northwest Pacific. So we're going back to the northwest of the North Pacific. We looked at average temperatures and salinities in a box up here, which are shown over here. This is SSS, and the winter data is in the bold lines for SST and SSS. And down here is the corresponding density, which is like the winter maximum density. And we kind of see these bidecadal cycles. And if we hold SST constant and only vary SSS, the density actually matches the total density pretty closely, and less so if we don't vary SSS but SST. So the conclusion from that is that most of the variation in winter maximum density is actually salinity driven and not temperature driven. About 85% of the variance can be explained by salinity. So, okay, SSA changes seem to be dominant. The next slide is going to be basically the same figure, but with linear trends on top of it. So these are the linear trends in density. The black one is the overall trend. Red and blue are the ones that can be associated with salinity and temperature. So here we find that salinity and temperature contribute about equally to the total. So it seems like the overall decline in density in the Northwestern Pacific is driven by SST and salinity changes. There has been papers out there how the North Pacific is freshening and also warming, of course. So finally, I wanted to come to the question about forcing from the Pacific decadal oscillation, which is like the dominant amount of variability that everybody has heard about in the North Pacific, other than ENSO. So the green line here is the PDO index, and the black line is again the density averages, winter density averages in this box that I have shown before. And the correlation is actually not very good. And we think this has to do with the fact that that the PDO is the leading principal component of sea surface, monthly sea surface variability in the North Pacific. And since much of these density changes are driven by salinity, in some ways it's not really surprising since the PDO is based on SST anomaly patterns and the surface density variations appear to be salinity dominated, that the correlation with the PDO is lacking in this case. So that already brings me to the final conclusions of our talk. So I think I hope I have shown that there is a significant correlation between isopycnal outcrop areas in the Northwest North Pacific and O2 oxygen downstream in the Northeast at about a 10-year lag, which makes sense in terms of travel times. What's kind of new is that the interdecadal variations in the outcrop areas are dominated by salinity variations. And there is another paper by O'Hara et al. Who kind of attributed this to atmospheric forcing that actually is coming from the Bering Sea into the Northwestern North Pacific. And the long-term trends in outcrop area reduction are driven both by freshening, decreasing salinity, and warming, increasing temperature trends in the North Pacific. And future work, there's always lots left to do. We plan on not looking only at outcrop areas, but also at subduction rates, time series of O2 content, lighter isopycnals, and other climate indices. So thank you very much.
Thanks a lot, Sabine. Very interesting talk and very convincing that salinity, again, is such an important variable here. We had a talk earlier today that dry regions become drier and fresh, wet regions wetter. Questions here from the audience? Marilou?
Thanks for the talk. So I have a question concerning the use of the satellite SSS data. As far as I know, this data concern really the skin salinity. And so my question is, how do you combine this information on the skin salinity with the information from in situ observation, which are usually more deeper in the ocean?
Well, we actually didn't use any. We didn't use any of the satellite salinity data, partly because the missions are relatively short. There were large biases in the data, and once the data were QC'd, and I don't know exactly whether it was the skin salinity or whether they adjusted it for subsurface, like 5 meters down salinity, but in the end we found when we looked at that product that it was almost the same as the Argo data, which kind of, at least in the North Pacific, which kind of tells you that it was tuned to the Argo data and doesn't really give that much more information, at least not for now. I mean, the hope, of course, is that in the future, satellite salinity can be used to monitor things like that a lot better.
Yeah, thanks a lot, Sabina. Also an excellent challenge for the modelers to use that data set that you have put together there and test the hypothesis, whether that models get that right as well. Thanks a lot, and we move on to the last speaker. Mathieu Poupon will also look at the decadal Pacific PDO that was already mentioned, and tell us all the rest about the impacts on the tropical Pacific.
Okay. Okay, thanks. Thanks everyone for being here after this long colloquium. So yeah, today I'll talk about the Pacific decadal oscillation and the fact that it influences the extension of the tropical oxygen minimum zone and obscures the impact of the anthropogenic change. So I may surprise you, but the tropical Pacific hosts an oxygen minimum zone. And well, a lot of us, we already introduced all the drivers of this oxygen minimum zone, but I will already just reintroduce what is interesting for me for this presentation. And so the oxygen minimum zone is maintained because of two factors. The first one is a weak ventilation, because the oxygen minimum zone is located in the zone that is called the shadow zone between the two support gyres. So it's not well ventilated. The renewable of oxygen is not efficient. And actually, most of the transport, I'll try to get my cursor. Most of the oxygen transport is realized by the equatorial undercurrent that you can see here, that is supplied by waters that are formed at mid-latitude, and that brings water from west to east inside of the oxygen minimum zone. So these waters are rich in oxygen. And the second factor is the high oxygen demand at the subsurface of the oxygen minimum zone that is tied to the high surface productivity. And so and so those oxygen minimum zones are variable in time, and we can think about their variability as a response to, there's a kind of two components in this variability. The first one is a response to the anthropogenic forcing that a lot of studies have tried to quantify, and another part is the response to the natural background variability of the Earth system. So here are the numbers of the estimates for the response to the anthropogenic forcing that are from the SROC report. So for those are the global numbers. For the subsurface, we observe the oxygenation that is about 2%, and we also observed global OMZ expansions. But I will also put your attention on the fact that there's high uncertainties associated with those numbers, and we are not really confident with the magnitude of those changes. And what we'll try to do today is to compare those magnitudes with the magnitude of the natural background variability that can happen in the tropical Pacific. I will only focus on the tropical Pacific. Those are the global numbers. And also try to go detail the mechanisms that are responsible for this natural background variability. And so also when we talk about natural background variability, there's a lot of scales, there's a lot of time scales, there's a lot of space scales. I will focus only on the decadal time scales in the tropical Pacific. So as you may know, the tropical Pacific is subject to a decadal natural variability mode that is called the Pacific Decadal Oscillation, or PDO, and that switch between positive and negative phases on decadal timescales, as you can see with this index that is based on the surface temperature, so we can track those changes. And what is the most important for us is that during the PDO phases, we observe a weakening of the subtropical circulation in the tropical Pacific, at mid-latitude and in the subtropical Pacific. And on the other hand, during the negative phase, we observe an intensification, a stronger subtropical circulation. And those changes can affect the OMZ dynamic by on two sides, a physical side and a biological side. And Dutay et al. In a paper published 4 years ago tried to investigate the impact of those changes. And they focused on the steady state solution in both phases for the two extreme case. So PDO plus, PDO positive PDO, and PDO negative. And they showed that during the positive PDO, because of this decrease in intensity of the circulation, we reduce the intensity of the ventilation by the equatorial undercurrent. So we supply less oxygen to the equatorial minimum zone, but also we decrease the intensity of the upwelling and nutrient supply to the surface. So we decrease the amount of organic matter exported at the subsurface and the oxygen demand. And it's the opposite during the negative PDO, the ventilation and oxygen demand increase because of the increase in intensity. And in the two cases, the ventilation changes, the physical changes, have a higher magnitude than the biological changes, so that in a steady state, for PDO positive condition, we observe large oxygen minimum zone, while for PDO negative condition, we observe small oxygen minimum zones. But in the ocean, there's no steady state, and the PDO oscillates between negative and positive phases on decadal timescales. So what I will try to do today is to see what happens if we consider the oscillating nature of the PDO. And I will try to answer those three questions. How do those oscillations modulate the oxygen dynamics and the OMZ volume in the tropical Pacific? How do the magnitudes of this natural variability and anthropogenic compares? And how do the models, because I will use models in this compare with the data that we have? To do so, to try to answer those questions, I used two models, two hindcast models, so MOM6 Cobalt with a ½ degree horizontal resolution, and Nemo Pisces with a 1 degree resolution. So they have like slightly better resolution, or horizontal resolution at the subsurface, at the equator, sorry. But they have like a slightly different physics because of their difference in resolution. And so those two models are forced with the same atmospheric product over 60 years, so that we can capture the last 3 PDO phases. So 2 negative and 1 positive. And before diving into the results, I just wanted to show you just some figures for evaluation of the model. So this is the time average to concentration at 400 meters in the World Ocean Atlas and in the two simulations. So we can see that there's pros and cons using the two models. MOM6 overestimates the anoxic core of the oxygen minimum zones, but because of this high spatial resolution, it reproduces a more realistic equatorial dynamic. It reproduces well the marine currents at the equator, while Nemo has like a better oxygen minimum, like OMZ volume distribution, but because of the poor resolution, it resolves not very well the dynamic. But as you can see, those two models represent the main features of the oxygen minimum zones. And now I will try to go to explain you how this varies into the white box how the oxygen concentration varies into the white box that you can see on the two figures. So first, let's look at the oxygen variations. So this is the two-time series of the integrated O2 content anomalies so it's integrated in the tropics between the first 1,000 meters, and we removed the linear trend to this data. So that's why it's an anomaly, the linear trend that can capture the anthropogenic changes, but also the drift that is associated to the models. And we also filtered the signals to keep only the variations that have the same time scales as the PDO using a filter. And so those two models in brown and red are doing have similar amplitudes, and what we can see is that we observe an oxygen gain during the PDO negative phase and an oxygen loss during the PDO positive phase. So now we can compare that with the variation of the OMZ volume, and so exactly the same process. We removed a linear drift, trend, and we filtered the signal. And here I'm also I'm showing you the picture of the volume of oxygen minimum zone for a threshold of 45 micromole per kilogram, just because I don't have the time to show everything, but the results are robust between 20 and more than 100 micromole per kg. And so here we observe that the volume contracts during the negative phase and expands during the positive phase, which is consistent with the oxygen concentration variation. So when you lose oxygen, your OMZ expands. When you gain oxygen, your OMZ volume contracts. And finally, I wanted to compare the amplitude of those oscillations with the amplitude of the trend, the linear trend that we removed. Because this linear trend can represent the deoxygenation associated with the anthropogenic forcing. And so it's important to compare how natural processes compare in magnitude to anthropogenic forcing. And as you can see, those numbers, in both cases, the anomaly of the amplitude is higher than the linear trend for the oxygen concentration and for the OMZ volume. So the PDO obscures the impact of the anthropogenic changes. And now I'll try to go quickly explain you the mechanisms. So we can split the oxygen signal into three terms. So a solubility term, a term that is the advective transport term, and the residual term that contains both the biology and the changes mixing. And so those are the. Sorry, I'm showing only the MOM6 results just for time because of time. Those three terms evolve over time, as you can see, and you can see that the advective transport variations amplitude dominate the oxygen signal, and the solubility and biology mixing counteract the advective transport and attenuate the oscillation amplitude by half. And I will not show you that today too, but the variability is mainly located in the equatorial band. So I'll just look at quickly the advective transport in the equatorial band. So that's the mean transport at the equator. So that's cross section of the oxygen equatorial transport, and as you can see, most of the oxygen is realized. Most of the oxygen transport is realized by the equatorial undercurrent. So that's the mean state. And when we look at the anomaly of this transport relative to the mean state during the PDO positive and negative phase, we observe that during the PDO we have a higher during the positive PDO we have a lower transport. During the negative PDO, we have a higher transport, which makes sense with the story I was discussing on the previous slides. And quickly, the last slide. I will not discuss the figure because I don't have the time, but we compared the mass transport in the models and the mass transport in the data that we have at the equator. And what we can see is that even if models reproduce quite well what we observe in the data. We observe higher variations in amplitude in the data than in models. So maybe the PDO effect can be larger in data than what we can expect from models. So to conclude, because of the oscillating nature of the Pacific decadal oscillation, during the PDO negative phases, we observe oxygen gain in the tropical Pacific and an OMZ contraction. And it's the opposite during the PDO positive phase. This is due to a modification of the OMZ advective oscillation intensity. And the results are robust for all threshold of, if you define an OMZ with a threshold between 20 and 160 micromole per kg. And by comparing with the data, the PDO impact may be higher than what is similarly seen by models. So all this presentation to say that the PDO obscures the impact of anthropogenic forcing. And it's something we need to take into account and to study more, because all the data we are using to estimate the trends of deoxygenation can be affected by those type of bias. Thanks very much. Oh, and sorry. before answering questions, I really wanted to thanks Andreas and Marie-Laure for the organization of this seminar, but also the student dream team that did like an amazing job for all of us to have this pleasant seminar. So thanks very much. I don't know where you are, but thanks.
Thanks, Mathieu, and wonderful last presentation here. And again, making it clear how important it is to bring models and data together, and theory and concepts as well. Very brief question. If there's one. Yes.
So as you pointed out, you've been given the last word. And what I think would be really important for us all to come away with is knowing just how many times the Brightberg figure was shown.
Yeah, okay. Yeah, I reported every time the Brightberg picture has been used in those slides all along the week. And I think we're around 25. So congrats everyone for like.
Thank you for that important insight.
Great, thanks. And we have a few new indicators as well, indices. Great. Okay, yes, thanks to all the speakers, all the audience here, and the organizers, the student team for this wonderful meeting, wonderful conference. We are not finished yet. We have a feedback of the early career scientists, I think, and I welcome you to enter the stage.
Where is it? Hello, good afternoon, everyone. Thank you very much for still being here. And thank you so much for the IT team for helping us. We cannot be here without you. And all the organizing team. So we are from Early Good Network. We try to collect some ideas from the young scientists that attending the sessions here and also online, and also our friends that, sorry. Okay. We try to connect our ideas, and also in these short presentations, we will try to present what we have been doing up until now. So here we go. So as we may have known that all the advanced ocean science that we have been doing up to this date, where we're still like early career scientists, we're still master students, but we got so inspired by the sessions that you have presented in these sessions. And we know that it will drive us to the Sustainable Development Goals, answering the goals that we need to achieve, be it in the climate action, the life below water, and also importantly, it's more partnerships for the goals. We need to work hand in hand with different sectors and also with different multi-stakeholders. And especially for the outcomes activities until 2030, we know that we have the GOOD program, which is the Global Ocean Oxygen Decade. And in this case, especially for the capacity building and ocean literacy. And we can especially for the Adapting Worldview citizen consultations, there are many initiatives that are on the ground. So we're looking forward to also establish the stakeholder to co-design approaches. And we will work in pair with GOND, IOC UNESCO. Thanks to GOND, we can be arriving at this point. And next. So a little bit glimpse, we are interdisciplinary network of young scientists. We're still opening for more young scientists to come on board with us because we know that we cannot do this alone, and the more is the better. And we work towards the Global Ocean Oxygen Decade and UN Ocean Decade for SDGs.
So our aims and objectives, we basically want to create a network and connect scientists, young scientists worldwide from around the world to create a global network in which we can collaborate with people from different disciplines and different masters, bachelors, up to PhD and postdoc. And we want to, through this network, to locate different research areas which need to be studied. And we want to also invest in our future scientists by identifying the problems that they face and try to find solutions and the support that they require in order to advance their research and to invest in better science. So to do this, to achieve these aims and objectives, we first started with trying to connect different scientists from around the globe. So we started creating networks through social media. We've created Instagram and Facebook. As you can see, they're very young still. We're still growing them. And we've been connecting a lot of people since then. Oh, for more information, we have a link tree in which we have more links to all our social media. So you can join. I encourage people to join. So with this, we have gotten a lot of information, a lot of data from different scientists, and we have been creating this map in which we can pinpoint areas and input different problems, different interesting research is happening, so different people can collaborate on these and put their ideas in here. Another thing is we've been creating a brainstorm whiteboard in which we have different areas in which we've been putting in the data from the different young scientists. So on the left-hand side, you can see what's happening right now, the past and the present. So the wind in our sails, what is interesting that's happening right now. So this is, people are really inspired that there is research being carried out on oxygen and deoxygenation. And then we have the problems, the anchors that are holding us back. So the problems that they have found or they have learned through this colloquium is that that social scientists are not really brought into the conversation. There's a lot of policy management which needs to be worked on, and different other mitigation tools, etc.
Yeah, and for the left side, we can see this is this sailboat metaphor. This is interesting because in this part, the pink part, we know that we can see what are our goals or what are the improvement that we can work towards. For example, we can see raising awareness with different approaches, and also they create a global research collaboration program that we think that it's still a big challenge, but we have a big opportunity to work on. And obviously for the better communication, we see today there's like panel media, and we know that we can actually create a better science by better scientists. They can also transform this science information into the general audiences. And we are also excited to the upcoming international summits. And the barriers that we see we know that we are working on the modeling, like most of the scientists that we have here also working on the modeling. We know that we can forecast some potential problems that can happen in the future. So in this part, we also try to visualize what kind of the problems that we can have, in which one of them is according to like data sharing, which is very still clashing with many conflict of interests, and global monitoring integrated data, which is actually, we have like a good news from the GOND that they will create, they will develop further the Go data. And of course, like some scientists are not being heard enough, maybe because we don't speak their language, the general audience's language, that actually are the one who can take part also the most on their daily lives. And the social issues that we need to be integrated with. Next. So our next initiative, the shortest one is going to be the podcast. So maybe some of you have heard this before, and we come up with the idea of name it with good vibe. Thanks to Gon as well, you inspired us from the good news. If you have a good news, you have a good vibe. So we will try to communicate the science in a more young generations way, in which up to date that according to what are we doing right now as the young generations, we will listen to some podcasts, and it's gonna be launched hopefully soon. So we were looking forward to collaborate with more scientists. We were also inviting some guests, like maybe from citizens that is not non-scientists. So this is the idea. How is the vibe that you can get the first time you heard the ocean deoxygenation, and after the conversations, what is the new vibe that you can feel right now? So that's still the general idea. So we're looking forward to further communicate this with you. Next. And of course, in the long run, we are looking forward to have more initiatives. Then, of course, we cannot do it alone, as we have said. So any more institutions that are being here right now, we are so open for more dialogues and for more networking. And we can have youth challenge, infield science outreach initiatives, and the other one.
So the questions that we still have left hanging, that we still have to answer is one, how can we future sustain this network? We've just started it, we've come to this conference, but what are the future initiatives for Early Good and this network? The next one is, how can we as early scientists, young scientists, be actively involved in policy making, in either the design or implementing it in the future? And how can we take part in future action?
And the last one would be, how can we take part in the upcoming ocean and climate-related conferences? Up to our exploration, we have the upcoming UN Youth Ocean Conference, and also the COP27, in which that, according to some observations, we know that the oceans issues still need to be standard out, and we need concrete actions to be voiced out. So we need to collaborate with multi-stakeholders that hopefully we can meet in the COP27. So, yeah. And this is our QR code for the network. Yeah. And thanks to these amazing scientists that we hit. Yeah. And also, yeah, this is the name. And of course, all the other anonymous young scientists, you know who you are. And yeah, that is all for now. We are open for like some minutes for questions and answers. And yeah, any feedback for you will be wonderful. Thank you.
Yeah, so it was also one of the aim of the colloquium. It was to engage with the young generation. And the idea that we had is to ask them to contribute actively to the building of this colloquium. And so that's, I guess that it has been a very good success. And for sustaining the network, we had a lot of discussion during the GONE meeting. So we have some suggestions and we will be back to you later with some ideas. So any comments? Yeah? Okay, so thanks. Thank you, Mattia. Thanks, Juan. Thank you.
I'm leaving the last word to you, so therefore I will do that now. On behalf of GONE, and I think on behalf of everybody here and who was here, thank you very much, Marie-Laure. I think we all know it was a huge effort, but it really paid back. Everybody was so happy and is so happy to be here in person and also online, and you did an awesome job. And so we just want to say thank you with some flowers.
Thank you so much.
And a tiny painting.
What's some reading?
No, it's a painting, actually. You can put it on the wall. You don't have to read. You read enough. That's just to look at it.
That's true. Thank you. Thank you so much. So thank you to the group. Yeah, thank you. Yeah, thank you. But that's really a group of work. And that's really cool. So I could read it. What did you find to find? And they were saying that it's very visible that I am an engineer because there is nothing on my office. So it's really what they say. It's yeah, very dry. And so now I will have this very nice thing. So thank you so much. And also it will also represent something. So it's just something that I would have bought in the office. So thank you very much. I will try to show it to you. But I cannot do everything. So it's wait a bit. Very nice. I like it very much. Voila. Yeah. The future. Yeah. It's correct. Yeah, very good. It's a very good. Ah oui. Okay, so I have to. I have to show it to it. So do you see? Yeah. So thank you so much. Yeah, I need to take the microphone. Thank you. So, yeah, so the closing, I would be very, very brief. Okay, so we will have the special issue in biogeoscience. So the deadline, they are here. We will send it to you again by email, but then the idea is to have a list of titles for the end of June, so preliminary title and preliminary list of authors. And then after, for early September, end of September, we will open the special issue for at least 6 months, probably 1 year, and eventually 1.5 years. This is how it works. So, and then I would like to remind you that we have the GONE webinar, and we really encourage you to submit IDs. So here you can see first the mailing list where you can sign up. And then you can also see the recording of the previous edition. And just if you want to propose a webinar, you just have to contact us. We would be very happy. Here it's some news from GONE. So we will have the good news starting in July, as you know. And if you have any suggestion, you can contact either Kirsten or Paul, who will work with us very soon. And so then, yeah, I would like to thank all these people here. So when we started to think to have this colloquium in present, but also in hybrid in January, when we had this GONE meeting, we did not realize to what we were committed, by the way. Really, I remember that they asked me, would you be able to do it in hybrid because to engage with everyone in the world? And so I say, yes, we have to try. Really, but then after it was really a challenge. And so all the people that you see here, they have been with me since January, meeting each week in my office and meeting an overview of the colloquium until today. So it's really a group effort, and we really want to have this meeting in presence because we felt that it was really needed to be together here, not only for science, but also for personal relationship. And I think that we were quite successful for that because we received very nice feedback about the colloquium, and we thank you so much for that. So thank you, and thank you to the team. Yeah, and thank you to all of you for coming, really. And so then you are probably wondering what would be the topic of the next colloquium. And so here it is. So it would be in May 8/4/12, and it would be about machine learning and data analysis in oceanography. Okay, and I don't know exactly the mode that who it will be organized, but it will be communicated to you later. So thank you so much, and have a safe back trip to your home, and thank you for coming. Bye-bye.